Without electricity, it would be nearly impossible to operate a process facility. Electricity is used to run motors that drive equipment, such as pumps, mixers, and air compressors. Electricity is also used for lighting systems, instrumentation and control systems, and heating and air conditioning systems. Traditionally, electricity has been defined as the result of a movement of electrons from one place to another. The electrons come from atoms. Atoms consist of three basic particles: protons, electrons, and neutrons. Protons have a positive electrical charge. Electrons have a negative charge. And neutrons don't have a charge. When an atom has the same number of electrons as protons, the positive and negative charges are balanced, and the atom is said to be electrically neutral. There are many forces in nature that can upset the balance of electrically neutral atoms. Any occurrence that causes an electrical charge imbalance, or in other words, anything that causes the number of electrons to be different from the number of protons, creates an electrical potential. An electrical potential is a situation that can lead to an electrical discharge. When an electrical discharge occurs, electrons or electrical charges move from one place to another. One example of an electrical potential is static electricity. Static electricity occurs when a large number of electrons builds up on a surface. A common cause of this type of buildup is friction. The buildup of electrons on a surface results in a high electrical charge and, consequently, a high electrical potential. When the potential is great enough, the electrons move or flow from one place to another. This flow of electrons is referred to as an electrostatic discharge. One of the most dramatic examples of an electrostatic discharge is lightning. Lightning occurs when atmospheric conditions cause a huge electrical potential to be built up between clouds and the Earth. When the charge imbalance is great enough, a tremendous arc forms that we call lightning. Electrostatic discharges are situations in which there's a momentary flow of current. Current can be defined as the movement of electrons or electrical charges from one place to another. For the vast majority of electrical equipment, a continuous flow of current is necessary for the equipment to operate. Now, with either an electrostatic discharge or a continuous current flow, there's movement of electrons. In order for this movement to occur, certain forces must be present. The forces related to the movement of electrons can be referred to as electromotive forces, or EMF. EMF is one way of expressing electrical potential. Another term that is used interchangeably with electrical potential is voltage. There are many sources of electrical potential. In this part, we'll focus on three: chemical action, heat, and light. Chemical action is the source of electrical potential that's at work in batteries. Whether the battery is a throwaway type or a rechargeable type, the basic elements are a set of electrodes and an electrolyte. The electrodes are generally some type of metallic material that becomes charged as a result of a chemical reaction. The electrolyte is the chemical that causes the necessary chemical reaction. Before the chemical reaction begins, both electrodes are electrically neutral. That is, they have an equal number of protons and electrons. The chemical reaction that takes place in a battery causes electrons to leave one of the electrodes. When this occurs, the electrode becomes positively charged. At the same time, the electrons build up on the other electrode, which becomes negatively charged. The oppositely charged electrodes create an electrical potential. If the electrodes are connected as part of a complete flow path, the electrical potential will cause a flow of electrons or current. A complete flow path is commonly referred to as a circuit. Another source of electrical potential is heat. One device that uses this source is a thermocouple. A thermocouple basically consists of two dissimilar metals that are joined together. When heat is applied to a thermocouple, the electrons in the metals move in such a way that an electrical potential develops. If the thermocouple is connected as part of a complete flow path, current flow will result, as indicated on this meter. As more heat is applied, the electrical potential and the resulting current flow increase. Since the amount of heat applied to a thermocouple is related to electrical potential, and therefore to current, thermocouples are most often used as temperature sensors in process systems. A third source of electrical potential is light. Light may be a great source of electricity in the future. The principle of producing electricity by using light is referred to as the photoelectric effect. Certain materials will generate electricity when they're exposed to light. For example, a solar cell contains this type of material. In fact, this solar cell can produce enough electricity to run a small motor. When the light intensity is increased, more electricity is generated, causing the motor to turn faster. Now, although chemical action, heat, and light are all sources of electrical potential, they're not sufficient or economical enough to supply continuous power for running electrical equipment. However, in certain applications, they can serve as important emergency power supplies. When magnetic effects are used to create an electrical potential, three elements are necessary. They are a magnetic field, a conductor, and relative motion between the magnetic field and the conductor. Let's begin with the magnetic field. Magnets have two poles, which are generally identified as north and south. When two magnets are placed close together, opposite poles will attract each other, and like poles will repel each other. The magnetic forces that cause these actions are invisible. They result from magnetic fields around the magnets. We can get an idea of what these magnetic fields look like with a simple demonstration. First, we'll place the magnets close together with the opposite poles next to each other. Next, we'll place a piece of paper over the magnets and sprinkle some iron filings on the paper. Notice that the filings are forming patterns or lines. The lines that are formed by the filings indicate magnetic force lines. The lines are usually referred to as magnetic flux lines. Now, as we said, a magnetic field is one of the three elements necessary to create an electrical potential. Another element is a conductor. A good conductor is a substance that provides a path through which current can flow easily. Copper and aluminum are examples of good conductors. Natural rubber and synthetic rubber are examples of poor conductors. A poor conductor, or insulator, is a substance that allows little or no current flow. Insulators are often used around conductors to prevent current from taking undesirable paths. The third element necessary to create an electrical potential is relative motion between the conductor and the magnetic field. Let's see what this means. This conductor is a coil of copper wire. It's connected to an electrical sensing device. The pointer on this device will indicate an electrical potential. If we move a magnet through the coil, we'll be able to see the effects on the scale. Notice that as the magnet moves through the coil, the indicator swings alternately between positive and negative. If the motion stops, the indicator moves back to zero. The same thing will happen if the magnet is held stationary and the coil is moved around it. That's what relative motion means. Either the conductor or the magnetic field has to move. The electrical potential that's created in this situation is usually referred to as an induced electrical potential. The conductor, the magnetic field, and the relative motion induce an electrical potential in the conductor. This is the basic principle behind the generation of electricity that's used to operate equipment in industrial facilities. When an electrical potential or voltage is induced in a conductor that's part of a complete circuit, current flows through the circuit. In many applications, the current flows first in one direction and then in the opposite direction. Current that changes directions in this way is called alternating current. Let's look at an example to see how alternating current can be produced. This demonstration includes a conductor in a stationary magnetic field. The conductor isn't moving, so there's no voltage and no current. To make what happens easier to follow, we'll represent the changes in direction on a graph. One axis on the graph represents the induced voltage, and the other axis represents time. As the conductor rotates through the magnetic field in a clockwise direction, the induced voltage first builds up from zero to a peak or maximum value in one direction. We'll call that direction positive. As the conductor continues to rotate, the voltage returns to zero. It then changes direction, builds up to a peak or maximum value in the negative direction, and returns to zero again. At this point, the voltage has completed a full cycle. This curve is called a sine wave. Now, in an actual power system, cycles occur rapidly. In many cases, there are 60 complete cycles each second. The unit that represents cycles per second is hertz, so 60 cycles per second can be referred to as 60 hertz. The value of the induced voltage is at a peak 2 times during each cycle. Since the value of the voltage is continually changing, the peak voltage value is not the true or effective value of the voltage that's produced during the cycle. Instead, the effective voltage is an average value. In most cases, the average that's used is called the root mean square, or RMS value. The term root mean square refers to the mathematical method that's used to calculate the average of the different voltage values in a cycle. For simplicity, the RMS value is usually given as 0.707 times the peak value. That's accurate enough for most situations. Well, we've seen how AC voltage is produced and how it changes, and we've seen how these changes can be represented by a sine wave. The sine waves we've looked at so far are single-phase sine waves. They represent power produced by single-phase generators. However, most large industrial equipment operates using three-phase AC power. Let's take a look at what this means. In this illustration, the conductor consists of three equally spaced coils or loops. As these loops rotate through the magnetic field, each loop produces voltage that can be represented by a sine wave. This illustration shows the voltage sine waves for the three loops. You'll notice that even though at individual times each sine wave becomes zero, the sine waves are never zero for two phases at the same time. This means that the effective voltage and current produced by this three-phase arrangement are never zero while it's operating. In this topic, we learned about electricity. We discussed electrical potential and some sources of electrical potential. We also covered magnetism and alternating current. Now try a few practice questions to check what you've learned. The forces related to the movement of electrons can be referred to as electromotive forces, or EMF. EMF is one way of expressing electrical potential. Another term that is used interchangeably with electrical potential is voltage. A third source of electrical potential is light. Light may be a great source of electricity in the future. The principle of producing electricity by using light is referred to as the photoelectric effect. To make what happens easier to follow, we'll represent the changes in direction on a graph. One axis on the graph represents the induced voltage, and the other axis represents time. As the conductor rotates through the magnetic field in a clockwise direction, the induced voltage first builds up from zero to a peak or maximum value in one direction. We'll call that direction positive. As the conductor continues to rotate, the voltage returns to zero. It then changes direction, builds up to a peak or maximum value in the negative direction, and returns to zero again. At this point, the voltage has completed a full cycle. Basically, a motor is a device that uses electrical energy to produce mechanical energy. Let's use a demonstration to understand this better. This is a very simple example of an electric motor. It consists of two bar magnets and a rotor. The rotor is the part of the motor that moves or rotates. The two bar magnets which do not move are called the stator. Copper conducting wire is wound around the arms of the rotor. The rotor is connected to a shaft. In order to operate, the motor must be part of an electrical circuit. In this circuit, a battery is the source of electricity, and a switch is used as a control device. When the switch is closed, a complete path is formed, and current flows through the conducting wire. As you can see, the rotor is spinning, causing the shaft to rotate. The motion results from the interaction between two magnetic fields. One of the magnetic fields is produced by the bar magnets. We'll call this field the stator's magnetic field. The other magnetic field is the rotor's magnetic field. It is a result of the current passing through the conducting wire. Whenever current passes through a conductor, a magnetic field is created around the conductor. This type of magnetic field is called an electromagnetic field. If the shaft in this motor were connected to a mechanical device, it could be used to drive the device. Motors come in many different sizes and designs. The variations allow motors to be used in many different applications. Regardless of the particular design of a motor, however, the principle of operation is the same for all motors. That is, the rotor's magnetic field interacts with the stator's magnetic field, causing the rotor to rotate. Direct current, or DC, is current that flows in one direction. In a DC motor, direct current flows through a conductor and creates a magnetic field around the conductor. This magnetic field interacts with another magnetic field to produce motion. Let's look at a demonstration to see how a DC motor operates. The stator, or stationary part of this model, is a horseshoe magnet. The rotor, or rotating part, is simply a coil of conducting wire wound around a metal core. A battery supplies electricity to the motor. When current flows through the rotor's coil, it causes the rotor to become an electromagnet. The attraction and repulsion between the poles of the horseshoe magnet and the poles of the rotor cause the rotor to turn. During operation, the rotor must continuously switch polarity in order to maintain motion. In other words, the north and south poles of the rotor must switch. The parts of the motor that cause the poles to switch are a commutator and brushes. The commutator in this arrangement is a small copper conducting cylinder that is split into two halves. These two contact strips that touch the commutator are the brushes. When the motor is operating, current flows from the negative side of the battery through one of the brushes, then through one half of the commutator and onto the rotor. After the current flows through the rotor, it flows to the other half of the commutator, then through the other brush. And finally, it returns to the positive side of the battery. The commutator and the brushes constantly change the direction of current flow to the rotor. That's what changes the polarity of the rotor. Now let's take a look at how the commutator, brushes, and rotor windings cause a DC motor to work. This horseshoe magnet is the motor's stator. The north and south poles are indicated by the letters N and S. The poles of the rotor are indicated in a similar way. When the rotor is in this position, the north pole of the rotor is repelled by the north pole of the stator and attracted by the south pole of the stator. Similarly, the south pole of the rotor is repelled by the south pole of the stator and attracted by the north pole. The combined effect of these attractions and repulsions moves the rotor. At this point, the commutator and brushes switch the direction of current flow through the rotor coil. The change in current flow direction switches the polarity of the rotor. This change in polarity keeps the rotor rotating in the same direction. It continually moves toward opposite poles. This continuous process of switching polarity causes the magnetic fields in a DC motor to change positions. That's what causes a DC motor to operate. An AC motor operates because of the interaction between the magnetic fields of its rotor and its stator. In most AC motors, alternating current is supplied to the stator windings. The current flow causes the magnetic fields around the stator windings to increase, decrease, and change polarity. Let's look at an example to see how the magnetic fields of the rotor and the stator interact in a simple AC motor. These two coils of wire make up the stator. This bar magnet is the rotor. It has a north pole and a south pole. When current flows through the stator coils, magnetic fields are created around the coils. Each magnetic field has a north pole and a south pole. In our example, we're starting with the north pole of the rotor next to a stator north pole and the south pole of the rotor next to a stator south pole. The like poles repel each other, so the rotor starts to rotate. As it does, its momentum and the attraction of its poles to the unlike stator poles help the rotation to continue. When the alternating current flowing through the stator coils reverses direction, the stator poles reverse. As a result, the like poles are next to each other again. The like poles repel each other, and the rotor continues to turn. This sequence will continue as long as the stator windings are being supplied with alternating current. A three-phase AC motor is more complicated than the example we just saw, but the basic principle of operation is the same. The interaction between the magnetic fields of the rotor and the stator cause the rotor to turn. This illustration represents the stator of one type of three-phase AC motor. This stator has 6 coils. There are 2 coils, or 1 coil pair, for each phase of alternating current. The coils are connected through a common point in what is called a Y connection, or a star connection. In this arrangement, the coil pairs for each phase are 120 degrees apart from each other. As alternating current flows through each coil pair, magnetic fields are created just like they were for the simple AC motor we looked at earlier. However, since there are 3 coil pairs, the stator always has 3 north poles and 3 south poles. As current flow through each coil pair increases, decreases, and changes direction, each magnetic field increases, decreases, and changes polarity. Because the coil pairs are 120 degrees apart from each other, the net effect through the complete three-phase cycle is that the overall magnetic field between the stator coils rotates. The rotor in this type of three-phase motor is an electromagnet. Its magnetic field interacts with the stator's rotating magnetic field, and as a result, the rotor turns. In this topic, we discussed electric motors. We learned about basic motor operation, and we discussed DC motor operation and AC motor operation. Now try some practice questions to check what you've learned. This is a very simple example of an electric motor. It consists of two bar magnets and a rotor. The rotor is the part of the motor that moves or rotates. The two bar magnets which do not move are called the stator. Now let's take a look at how the commutator, brushes, and rotor windings cause a DC motor to work. This horseshoe magnet is the motor's stator. The north and south poles are indicated by the letters N and S. The poles of the rotor are indicated in a similar way. When the rotor is in this position, the north pole of the rotor is repelled by the north pole of the stator and attracted by the south pole of the stator. Similarly, the south pole of the rotor is repelled by the south pole of the stator and attracted by the north pole. The combined effect of these attractions and repulsions moves the rotor. At this point, the commutator and brushes switch the direction of current flow through the rotor coil. The change in current flow direction switches the polarity of the rotor. This change in polarity keeps the rotor rotating in the same direction. It continually moves toward opposite poles. The rotor in this type of three-phase motor is an electromagnet. Its magnetic field interacts with the stator's rotating magnetic field, and as a result, the rotor turns. A process plant is made up of many systems and many different types of equipment. All of the systems and equipment work together to produce a product. The operation of plant systems and equipment is based on scientific principles. Understanding these principles will give you a better idea of what's going on in the plant. For example, if you understand the principles of heat transfer that enable a heat exchanger to heat or cool fluids, you will be better able to determine whether a particular heat exchanger is operating properly. And if you understand the principles of fluid dynamics, you'll know that when the flow rate in a system changes, the pressure in the system also changes. Some of the physical properties that we measure are referred to as dimensions. The fundamental dimensions are length, time, and mass. These three dimensions and the units associated with them are the basis for many of the measurements that are made in a plant. Two standard unit systems that are commonly used to measure the fundamental dimensions are the English system and the metric system. We'll use the English system for this discussion. The standard unit of length in the English system is the foot. All other measurements of length in this system, such as inches, yards, and miles, are based on the foot. Length is a basic measurement that is used to derive several other measurements, such as area and volume. Area is a measure of a two-dimensional surface, and volume is a measure of a three-dimensional object or space. Let's use this brick to see how length measurements are used to calculate area and volume. For our discussion of area, we'll focus on this surface. This length measurement is 2 inches, and this one is 4 inches. The area is calculated by multiplying these two measurements together. So 2 times 4 is 8. Since area is a two-dimensional surface, it is expressed in square units. For this example, since both sides were measured in inches, the area measurement is expressed in square inches. Other units of area, such as square feet, square yards, and square miles, would be calculated the same way. The volume of a rectangular solid, like this brick, can be calculated by multiplying 3 length measurements together. As we just saw, this surface is 2 inches by 4 inches. The third measurement is 8 inches. So 2 times 4 times 8 equals 64. Since volume is a three-dimensional measurement, it's usually expressed in cubic units. In this case, cubic inches. Cubic feet and cubic yards are also common units of volume and are calculated the same way. The volume of this object can be calculated by multiplying 4 feet times 5 feet times 12 feet, for a total of 240. Since the three length measurements are all in units of feet, the volume is expressed in cubic feet. Now, using length measurements to calculate the volume of a solid is not the only way volume is expressed. Volume is also used in measurements of fluids. The standard unit of fluid volume measurement is the gallon. A gallon is not a measurement based on length, but both cubic feet and gallons are used to measure volume. 1 cubic foot does not equal 1 gallon. This 1 cubic foot container actually holds 7.48 gallons of water. If we empty these gallon jugs into the cubic foot container, it should take just about 7.5 jugs. And that's about what it takes. This is not the only example of a situation where more than one unit can be used to measure the same thing. For this reason, conversion tables, or standard equivalence tables, are available to help you find measurements and their equivalents in other units. Although the second and the minute are 2 units of time that you're most familiar with, flow rate and velocity are both derived from units of time. Flow rate can be measured in units derived from a combination of a unit of volume and a unit of time. Flow rates are used to measure the amount of fluid passing a particular point over a period of time. A typical unit of flow rate is gallons per minute, or GPM. For instance, this flow meter is indicating approximately 2.2 GPM. In other words, there are 2.2 gallons of water passing this point in the system every minute. Velocity is a measurement that is derived from a unit of length and a unit of time. Velocity is the distance traveled over a period of time, and it is often measured in feet per second. The third fundamental dimension is mass. Mass can be defined as the amount of matter an object possesses. But mass is not measured directly. The most common method of measuring the mass of an object is by weighing it. The standard unit of weight in the English system is the pound. The weight of an object is the result of the force of gravity acting on the mass of the object. Like weight, mass can be measured in pounds. On Earth, an object that has 1 pound of mass weighs 1 pound. As you may know, most of the measurements taken in a plant are related to process variables. The most common process variables measured are pressure, temperature, flow, and level. Let's discuss the units related to measuring process variables, beginning with pressure. Pressure is defined as force applied over a unit area. It's measured in units of force divided by units of area. Pressure is usually measured in PSI, pounds per square inch. To illustrate this, let's say we have 10 pounds of pressure applied over a 1 square inch area. We have 10 pounds per square inch. 10 pounds of pressure divided by 2 square inches is 5 pounds per square inch. In a plant, pressure is often indicated on a gauge, like this one. This gauge is indicating about 156 psi. In other words, the pressure at this point in the system is about 156 pounds per square inch. Temperature is another important process variable. Temperature is an indication of the relative hotness or coldness of a substance. The most common unit of temperature in the English system is degrees Fahrenheit. Like pressure, temperature is often measured at various points in a system. For example, this temperature gauge is indicating that the temperature at this point in the system is 232 degrees Fahrenheit. Flow rate is another process variable that is measured in plant systems. Flow rate is defined as the amount of fluid that passes a particular point in a system in a certain unit of time. Generally, flow rates can be measured in mass flow units or in volume flow units. This recorder indication is an example of one common mass flow unit, pounds per hour. On the other hand, volume flow rates are typically measured in gallons per minute or cubic feet per second. The last process variable we'll discuss is level. Level can be defined as the position of a surface above or below a fixed reference point. For instance, in this illustration, if the reference point is at the bottom of the tank, measurements are taken from the bottom to the surface, indicating how much of the tank is filled. If the reference point is at the top of the tank, measurements are taken from the top to the surface, indicating how much of the tank remains to be filled. Another way the level in this tank can be expressed is as a percent of maximum height. For example, the level in this tank is at the halfway mark, so we can say that the level is 50% of maximum height. Level is usually measured in units of length. For example, the scale on this tank is indicating the level in feet and inches. In this topic, we looked at the fundamental dimensions of length, time, and mass, and we identified some units that can be used to measure these dimensions. We also saw that many other measurements can be derived from these fundamental dimensions. We also saw that some measurements can be expressed in several different ways. For example, we saw how a volume measurement can be expressed in gallons or in cubic feet. Conversion tables help us express measurements in different units. Since most of the measurements that are made in a plant are related to process variables, we discussed the four process variables that are most commonly measured: pressure, temperature, flow, and level. And we identified the units of measurement that are generally used to measure these process variables. Now take time and try some practice questions. Length is a basic measurement that is used to derive several other measurements, such as area and volume. This recorder indication is an example of one common mass flow unit, pounds per hour. On the other hand, volume flow rates are typically measured in gallons per minute or cubic feet per second. Let's begin our discussion of force and motion by defining a few terms. Force can be defined as a push or pull on an object. For example, weight is the result of gravitational force which pulls all objects toward the center of the earth. Like gravity, all forces are invisible. For example, if we sprinkle iron filings on a piece of cardboard and move a magnet underneath the cardboard, the filings move because of magnetic force. But we can't actually see the force. In this case, what we can see is the action that results from the force. This resulting action is called motion. Motion can be defined as a body changing position. Applied forces can have several effects on motion, including starting a motion, changing the direction of a motion, or stopping a motion. For example, many process systems operate with fluid flowing through them. The flow in these systems does not simply start and stop. Instead, forces are often applied by pumps to start the flow, and forces are applied by valves to regulate the flow. So you can see why force and motion are important considerations in the operation of a process plant. Let's take a look at three basic laws of force and motion. Going over them can help you see how force and motion are related. The first law states that when an object is not moving, It won't start moving unless a force is applied to it to overcome its inertia. Inertia is a property of matter that resists changes in motion. An object that's not moving remains at rest because of its inertia. And when an object is moving, its inertia causes it to continue moving in a straight line unless a force is applied to it. Inertia relates directly to the mass of an object. So the greater the mass of an object, the greater the inertia. And the greater the inertia, the greater the force required to start an object moving, stop a moving object, or change a moving object's direction. Now, the second law deals with the applied force. Simply stated, the second law says that force, F, equals mass, m, times acceleration, a. Acceleration can be defined as the rate of change in velocity over a given unit of time. A change in velocity may cause an object to either speed up or slow down. So basically, acceleration is a measure of how fast an object changes speed. That is, either speeding up or slowing down. For example, as a result of an applied force, this ball accelerates from zero velocity to its peak velocity. To understand this better, let's look at the action again, but this time we'll use a scale to show distance and a clock to show time. If the ball moves 2 feet in the first second, 4 feet in the second, and 6 feet in the third, it travels an additional 2 feet for every second that passes. In other words, it accelerates at a rate of 2 feet per second, Feet per second, or simply feet per second squared, is a common unit of acceleration. Just about anywhere there's motion, the relationship of force, mass, and acceleration is applied. In the flow of fluid, in the movement of solids, or in a moving vehicle. A good example of the first two laws at work in the plant can be seen in a pump startup. Here's a cutaway illustration of a centrifugal pump. We'll slow down the action so that we can explain what's happening. Before the pump is started, the fluid in the system is at rest, and its inertia tends to keep it there. The fluid has a velocity of 0. When force is applied by the pump, the fluid starts moving. The applied force causes the fluid to accelerate from 0 velocity to its final velocity. Once the fluid reaches its final velocity, the applied force and the fluid's inertia will keep it moving at a relatively constant speed. In this case, although the fluid starts at rest with 0 velocity, applying a greater force causes its acceleration to be greater and its final velocity to be greater. The third law of force and motion we'll look at states that for every action, there is an equal and opposite reaction. In other words, if a force is applied to an object, the object applies a force that's equal, but exactly opposite in direction. This law is usually referred to as the action-reaction law. The force that lifts and moves a rocket into space is the reaction force that results from rapidly moving gases that are created by the combustion of fuel. In the plant, an example of the third law can be seen in this demonstration using a compressed air hose. The movement of the hose is caused by a reaction force that's produced when air flows rapidly out of the hose. Another example is the pipe supports that keep pipes from moving when the fluid flowing through them makes a turn. As the fluid makes the turn, the pipe exerts a force on the fluid, and the fluid exerts a reaction force on the pipe, causing it to try to move in the opposite direction. So the three laws give us a means of analyzing forces and motions. In this topic, we looked at force and motion. We saw how force and motion are related, and we discussed three laws of force and motion. Nearly every aspect of plant operation is affected by force and motion, so it's important for you to have an understanding of the concepts that we covered. Now try some practice questions. Force, like the force that pushes this ball, can be defined as a push or pull on an object. Because of the applied force, The ball is in motion. Motion can be defined as a body changing position. Gravity is a force that acts on all objects on Earth. Gravity exerts a downward force or pull toward the center of the Earth. Now, the second law deals with the applied force. Simply stated, the second law says that force, F, equals mass, m, times acceleration, a. This ball is in motion because a force was applied to it. What would happen if a greater force were applied in the same way? What force causes these boxes to fall to the ground? In a plant, various pieces of equipment, such as pumps, tanks, and heat exchangers, are connected by piping in groupings called systems. Systems that contain liquids or gases are commonly referred to as fluid systems. To ensure that plant processes operate smoothly and efficiently, it's important for operators to understand how these systems function. In a plant, many different pieces of equipment work together to perform one or more jobs. Any group of connected components that function together to carry out a specific task can be referred to as a plant system. For example, this steam generating system provides the steam that's used by this plant. Like most systems, the steam generating system is made up of several smaller systems or subsystems. For example, it has a fuel subsystem to supply fuel to a boiler, a steam distribution subsystem to transport steam from the boiler to plant equipment, and an instrumentation and control subsystem to monitor and control operating conditions. Many plant systems are fluid systems. By definition, a fluid is anything that flows, but in general, fluids are liquids and gases. For example, the water in this discharge channel is a fluid, as is the flue gas flowing from this stack. Slurries, which consist of solids mixed in liquids, can also be classified as fluids. The operation of a fluid system can be affected by different factors. One of the most important of these factors is pressure. One form of pressure is illustrated in this simplified fluid system. Here, a non-moving or static liquid, in this case water, exerts pressure on a gauge mounted near the bottom of a container. The pressure exerted by a static liquid is known as hydrostatic pressure, and it's related to the depth and density of the liquid. So the hydrostatic pressure exerted on the gauge varies with the level of the water. As it turns out, every inch of water above the measurement point corresponds to a pressure of 0.0361 pounds per square inch, or psi. Every foot of water corresponds to a pressure of 0.433 psi. Now, in order for a fluid to flow in a system, certain pressure conditions must exist. This fact can be illustrated using this U-shaped tube that contains a liquid. Both ends of the tube are open, so atmospheric pressure is applied equally to the surface of the liquid in each leg of the tube. Since the pressure is the same in both legs, there's no flow, and the level in each leg is the same. But if additional pressure is applied to one leg of the tube, the liquid in that leg is forced downward, while the liquid in the other leg rises. In other words, the liquid flows because of the difference in pressure that's applied to the two legs. A fluid system is made up of components that function together to perform a specific task. To accomplish its task, a system must have at least 4 basic parts to satisfy certain key requirements. For example, a system must have an energy source to provide the energy necessary to carry out the task, a transmission path to transport the energy or process medium from one place to another, one or more control devices to adjust or change operating conditions in the system, and one or more components that carry out the specific task of the system, and in doing so, create a demand or load on the system. While the basic requirements of a fluid system can be divided into these 4 categories, the components that help satisfy those requirements often fall into more than one category. For example, a control device may also be considered part of the transmission path. To get a better understanding of how a fluid system is structured, let's look at how the requirements of a liquid system are met. In a liquid system, the energy that's needed to perform a task is often supplied by a pump. A pump adds energy to the liquid and creates flow. Two types of pumps commonly found in liquid systems are positive displacement pumps and centrifugal pumps. While these pumps operate differently, they both cause flow by creating a pressure difference in the system. Generally, if a pump in a liquid system is not operating, there's no pressure difference in the system, so there's no flow. But when the pump is started up, pressure changes will occur. When the pump is started up, the pressure at the inlet or suction of the pump decreases, while the pressure at the outlet or discharge of the pump increases. As a result, liquid is drawn into the low pressure area at the suction of the pump, then discharged at a higher pressure from the outlet of the pump, causing flow through the system. While pumps commonly serve as the energy source for liquid systems, other components can share that responsibility. For example, a heat exchanger may function as an energy source if it adds heat or thermal energy to a liquid. But regardless of the component that's used, the basic requirement is the same. The system must have an energy source. Another basic requirement of a fluid system is to have a transmission path to move fluid from one place to another. In a liquid system, the transmission path is made up of components that the liquid flows through, such as pipes, valves, and tanks. Control devices are also needed by a fluid system. They're basically mechanisms that adjust or change the operating conditions of the system. Control devices for a liquid system typically include control valves that start, stop, or regulate flow, as well as instruments that monitor and control operating conditions. Adjusting control valve settings is a common way to control the flow rate in a system equipped with centrifugal pumps. But besides changing flow, these adjustments may also affect other variables in the system. Adjusting control valve settings to change flow will also affect pressure, since flow and pressure are so closely related. The way that the discharge pressure of a pump varies with flow can be illustrated using this graph. On the graph, the horizontal axis represents flow rate. Here, the flow rate is given as a percentage of the pump's capacity, but it's often represented in gallons per minute. The vertical axis of the graph represents the discharge pressure. If the pump is running and the control valve is fully closed, the discharge pressure is at its maximum value for the pump's speed, while the flow rate is zero. As the valve opens, the flow rate increases and the discharge pressure decreases. When the valve is fully open, the flow rate is at its maximum value, while the discharge pressure is at its minimum value. The curve that's formed on the graph is sometimes called a pump characteristic curve. Basically, it provides a way to see how a pump's discharge pressure is affected by different flow conditions. The fourth basic requirement of a fluid system involves carrying out the specific task of the system, and in the process, creating a demand or load on the system. In a liquid system, the components that fulfill the load requirement are often heat transfer devices. For example, this condenser carries out the specific task of a cooling water system. It removes heat from a vapor in another system. Inside the condenser, heat is transferred from the hot vapor to the cooling water that flows through tubes inside the condenser. The condensation process causes the vapor to change into a liquid. If the flow rate or the temperature of the vapor increases, more heat has to be removed from it. Under these circumstances, the cooling water system must be able to supply more water to absorb more heat, so the load on the system increases. If the flow rate or the temperature of the vapor decreases, less heat has to be removed, so the cooling water system doesn't need to supply as much water. In this case, the load on the cooling water system decreases. In a plant system, energy is converted from one form to another so that the system can perform its task. An important principle that's associated with the conversion of energy in a system is the law of energy conservation. The law of energy conservation states that energy can neither be created nor destroyed, only altered in form. This means that all of the energy in a system can be accounted for. The total energy that's present at any given point in a fluid system consists of different forms of energy, including thermal energy, which is energy related to the amount of heat in the fluid; kinetic energy, the energy related to the motion of the fluid; potential energy, the energy related to the position or elevation of the fluid, and what we'll call flow energy, the energy related to the pressures associated with fluid flow. Based on the law of energy conservation, as long as no energy enters or leaves a system, any change in the amount of one form of energy at a given point in the system will result in a change in one or more of the other forms of energy. Let's see how this works. This illustration represents a section of liquid system piping with a restriction in it. Two pressure gauges are mounted on the piping, one just upstream from the restriction and one directly in the restriction. Once flow is established in the system, the flow and pressures settle out to steady state conditions. In other words, conditions in the system remain constant over a period of time. Under these conditions, the pressure indicated by the gauge mounted in the restriction is less than the pressure being indicated by the upstream gauge. This difference in pressure occurs because at the restriction, the flow area is smaller. Now, we said that the energy related to the motion of a fluid is kinetic energy, and that the energy related to the pressures associated with fluid flow is flow energy. With that in mind, we can say that the energy conversion that's taking place at this restriction is a conversion of flow energy to kinetic energy. In other words, the liquid's pressure decreased, but its velocity increased. In the example we just looked at, flow energy was converted to kinetic energy. But at other sections of a liquid system, different types of energy conversions take place. For example, here's a section of piping in which two pressure gauges are situated at different elevations. The flow area of the pipe at the two gauges is the same, but the pressures being indicated by the gauges are different. In this section of piping, the decrease in pressure results from an increase in elevation. As we said earlier, the energy related to the position or elevation of a fluid is potential energy, and the energy related to the pressures on the fluid is flow energy. So the energy conversion that's taking place in this section of piping is a conversion of flow energy to potential energy. In general, energy conversions that occur within a liquid system have no effect on the total amount of energy in the liquid. But energy sometimes enters or leaves a system as well, and these energy transfers, as they're called, do affect the total amount of energy in the liquid. One device in which energy transfers commonly take place is a cooler. The purpose of this particular cooler is to transfer heat from a hot process liquid to cooling water. The hot process liquid enters the cooler here, flows through what is known as the shell side of the cooler, and exits here. At the same time, the cooling water enters here, flows through the tubes in the cooler, and exits here. As the process liquid makes contact with the cool tube surfaces, heat is transferred from the liquid through the tubes to the cooling water. The thermal energy that's transferred out of the process liquid causes the total energy in the process liquid to decrease. And since the same amount of thermal energy goes into the cooling water, the total energy in the cooling water increases. Energy transfers and energy conversions occur continuously in fluid systems. Sometimes these energy conversions are enormous. For that reason, there are some precautions associated with fluid system operation. For example, it's important that flow control valves in a liquid system be properly adjusted to prevent changing flow through the system too rapidly. The energy conversion from a rapid flow change can create a pressure pulse that travels through the entire system. When the pulse encounters bends or restrictions in the piping, it slams into them, causing a shock to the system known as water hammer. In severe cases, water hammer can cause piping to rupture, or it can damage other system components. By following operating procedures, you'll stand a better chance of avoiding these types of problems. In this topic, we examined some general information about plant systems and fluids, and we described the basic structure of a liquid system. We also described energy conversions that occur in a liquid system. Now let's try some practice questions. In a plant, many different pieces of equipment work together to perform one or more jobs. Any group of connected components that function together to carry out a specific task can be referred to as a plant system. Control devices are also needed by a fluid system. They're basically mechanisms that adjust or change the operating conditions of the system. Control devices for a liquid system typically include control valves that start, stop, or regulate flow, as well as instruments that monitor and control operating conditions. When a constant flow of liquid passes through this narrowed section of pipe, the pressure of the liquid decreases and the velocity of the liquid increases. Different types of gas and vapor systems can be found in process facilities. Although these systems may look different and serve different purposes, they each have to have at least 4 basic parts to satisfy certain key requirements. For example, a gas or vapor system has to have an energy source to provide the energy necessary for the system to perform its task, a transmission path to transport the gas or vapor from one place to another, control devices to adjust or change operating conditions in the system, and components to carry out the specific task of the system, and in doing so, create a demand or load on the system. The basic structure of a gas or vapor system can be illustrated using a compressed air system. In a compressed air system, the energy source is normally an air compressor. The air compressor adds energy to the system in the form of increased pressure. The transmission path for the system is made up of all of the components that contain the compressed air, including the piping and hoses that connect the components in the system, as well as a tank called a receiver that stores pressurized air for systems and equipment. Control devices which adjust or change operating conditions in the system typically include valves and regulators that help control the flow and pressure of the compressed air. Instruments that monitor variables in the system are also examples of control devices. The compressed air system also has components that use the compressed air to carry out the system's function. As they do, they create a demand or load on the system. In this system, these components include air-driven or pneumatic actuators and pneumatic tools. Now try a question about the structure of a compressed air system. This actuator is part of a compressed air system. It uses air to position a valve that controls the flow of liquid in a pipe. Which basic part of the compressed air system is the actuator's operation associated with? Many of the gas and vapor systems in process plants have similar features. For example, many of them have pressurized storage tanks or pressurized cylinders to store the gas. Also, gas and vapor systems commonly use valves to control the flow of gases from the containers. Another component that's used in liquid as well as gas and vapor systems is a jet pump. A jet pump uses the flow of one fluid to move another fluid. An air ejector that uses steam to remove air and other non-condensable gases from a condenser is one type of jet pump. There are no moving parts inside a jet pump. Instead, the pump relies on energy conversions to operate. The jet pump shown here has a nozzle, a pump inlet, a combining chamber, and a discharge section. During operation, high-pressure steam flows into the nozzle inlet of the jet pump and passes through a restriction in the nozzle. This causes a low-pressure area to form just past the nozzle. The low pressure draws the gas being pumped in through the pump inlet and into the combining chamber where it combines with the steam. The mixture then flows out of the jet pump through the discharge section. So in a jet pump, flow energy, that is energy that's related to pressure, is converted to kinetic energy in the nozzle, and the decrease in pressure that results from this conversion is used to pump the other fluid. Now, another device found in some gas and vapor systems is a condenser. Its purpose is to convert a vapor into a liquid by transferring energy. Inside a condenser, the vapor comes in contact with cool surfaces. In most condensers, the cool surfaces are tubes through which cooling water flows. Heat transfer takes place between the hot vapor that comes in contact with the tubes and the water that's flowing through the tubes. As a result, heat transfers out of the vapor, causing the vapor to condense to a liquid. As the vapor condenses, its volume decreases, creating a low pressure area. The drop in pressure draws more vapor into the condenser and enables the process to continue. Now, even though the low pressure inside a condenser is necessary for it to operate, it can also lead to some undesirable conditions. For example, there's always a chance that air will be drawn in through leaks or with the vapor flow. Air won't condense, and if it's allowed to build up, it can eventually fill the condenser and stop the flow of vapor. If this occurs, the condenser is said to be airbound. To prevent this problem from occurring, air removal systems, such as an air ejector, are normally connected to a condenser. A similar problem can occur if the condensed liquid isn't removed. As with air, if the liquid is allowed to build up, it can eventually block the flow of vapor. In this topic, we described the basic structure of one type of gas and vapor system, and we examined the operation of various gas and vapor system devices. Now let's try some practice questions. The basic structure of a gas or vapor system can be illustrated using a compressed air system. In a compressed air system, the energy source is normally an air compressor. The air compressor adds energy to the system in the form of increased pressure. Another component that's used in liquid as well as gas and vapor systems is a jet pump. A jet pump uses the flow of one fluid to move another fluid. An air ejector that uses steam to remove air and other non-condensable gases from a condenser is one type of jet pump. There are no moving parts inside a jet pump. Instead, the pump relies on energy conversions to operate. Virtually all industrial processes make use of gases and flowing liquids. To better understand these processes, operators need a basic knowledge of their operating principles. Compared to solids and liquids, the molecules of gases are spaced far apart. Also, there are virtually no cohesive forces between the molecules to hold them together, so they can move around freely. As a result, gases do not have a definite shape or volume. To keep their free-moving molecules from escaping, gases are normally stored in sealed containers. The temperature and pressure of a contained gas are directly related to the molecular motion in the gas. In general, temperature is the relative hotness or coldness of a substance. But at the molecular level, temperature is a measure of the molecular kinetic energy of a substance. Kinetic energy is the energy of motion, so temperature is related to molecular motion. Now, pressure is the amount of force exerted over a given area. Let's consider a particular area of this container. The pressure exerted by a gas results from collisions between the molecules of the gas and the walls of the container. If the number of collisions increases, the pressure also increases. This can be accomplished by compressing the gas or by increasing its temperature. For example, if the temperature of the gas increases, the kinetic energy of the gas molecules also increases. In other words, the molecules are moving around faster. This also affects pressure. For a given area of the container, there are more collisions between the gas molecules and the container walls, so the pressure also increases. In a contained gas, the properties of temperature, pressure, and volume are related. If a change occurs in any one of these three properties, the change will affect one or both of the other two. The ways in which gas temperature, pressure, and volume relate to each other have been formulated into three laws: Boyle's law, Charles's law, and the general gas law. Boyle's law deals with the relationship between the pressure and volume of a gas. Boyle's law states that at a given temperature, the pressure of a gas varies inversely with its volume. So if the volume of the gas decreases, its pressure increases. If volume increases, pressure decreases. We'll use this gas-filled container to illustrate Boyle's law. We'll assume that the temperature of the gas doesn't change. The pressure in the container is related to the number of collisions between the gas molecules and the walls of the container. As the molecules collide with the walls, a force is applied over the surface area. With less volume, the gas molecules are squeezed into a smaller space, so there's less space between the molecules. As a result, there are more collisions between the molecules in the container. With more collisions in a given area, there's an increase in gas pressure. While Boyle's law deals with pressure and volume, Charles's law deals with temperature and volume. According to Charles's law, at a given pressure, the volume of a gas varies directly with its temperature. That is, as temperature increases, volume increases. As temperature decreases, volume decreases. When the gas in the balloon is cooled, the volume of the gas decreases. As the volume decreases, the balloon shrinks. If the temperature of the gas in the balloon is increased, the volume of the gas also increases, so the balloon expands. We've seen how the pressure and volume of a gas react at a given temperature, and we've seen how the temperature and volume of a gas react at a given pressure. Now let's see how a gas reacts when all three properties are allowed to vary. We'll use this piston and gas-filled cylinder to illustrate the relationship. If a gas is confined in a given volume, and then the volume is decreased, there are more collisions between the gas molecules and the cylinder and piston. This produces an increase in gas pressure. If the volume of a gas decreases, the temperature of the gas increases because there's more molecular motion in a smaller area. This is a basic operating principle in an air compressor. Air is compressed into a smaller space. As the volume of the air is decreased, its pressure and temperature increase. If the temperature in an air compressor gets too high, it can lead to serious operating problems. To keep the temperature of compressed air from getting too high, air coolers are typically used with air compressors. One way to express the relationship between gas temperature, pressure, and volume is in a formula known as the general gas law, or ideal gas law. According to this formula, pressure times volume divided by temperature equals a constant value. This formula requires absolute units for pressure and temperature. Whenever there is a change in one of the three variables, pressure, volume, or temperature, the remaining two variables will change so that the value of the constant doesn't change. In this topic, we looked at some of the important properties of gases. We saw how changes in one gas property can affect others, and we looked at various gas laws. Take a minute now to do a couple of practice questions. If the temperature of the gas increases, the kinetic energy of the gas molecules also increases. In other words, the molecules are moving around faster. This also affects pressure. For a given area of the container, there are more collisions between the gas molecules and the container walls, so the pressure also increases. If the volume of a gas decreases, the temperature of the gas increases because there's more molecular motion in a smaller area. Many plant pressure measurements are based on atmospheric pressure, so operators need to be familiar with the basic principles behind atmospheric pressure. The atmosphere, or air, is a mixture of gases that surrounds the Earth to a depth of several miles. The air has weight because gravity pulls the air toward the Earth. The weight of the air exerts a pressure on the Earth's surface. This is what we call atmospheric pressure. Atmospheric pressure is related to height or depth. That is, the pressure of the atmosphere varies with the height of the air above the Earth's surface. For instance, atmospheric pressure at sea level is greater than atmospheric pressure at higher altitudes. At sea level, standard atmospheric pressure is 14.7 pounds per square inch, or psi. At higher altitudes, there is less air pushing down, so the weight of the air is less, and the pressure of the air is less. We can show how atmospheric pressure is measured with an illustration. This is a barometer that has a sealed tube filled with mercury and a bowl. When the bottom of the tube is unsealed, mercury flows from the tube into the bowl. The weight of the column of mercury exerts pressure, and the atmosphere also exerts pressure. Flow stops when the pressure exerted by the weight of the mercury in the tube equals the opposing pressure exerted by the atmosphere on the mercury in the bowl. In other words, the mercury will flow until the pressure exerted by the mercury column is equal to atmospheric pressure. You can determine how much pressure the atmosphere is exerting by measuring the height of the mercury column. At sea level, atmospheric pressure can support the weight of a column of mercury that's about 30 inches high. So atmospheric pressure is equivalent to the pressure exerted by a column of mercury 30 inches high. The height of a column of liquid that atmospheric pressure can support depends on the type and density of the liquid. For example, water is much less dense than mercury. Atmospheric pressure can support a column of water that's about 34 feet high. Atmospheric pressure is commonly expressed in terms of inches of mercury or pounds per square inch. Specifically, standard atmospheric pressure equals 30 inches of mercury or 14.7 psi. A commonly used pressure measuring device is a manometer. Manometers use columns of liquid to measure pressure. This example is a U-tube manometer that's designed to measure pressure inside a container. The manometer is partially filled with liquid and connected to a container that's open to the atmosphere. The atmospheric pressure on each column of liquid is the same. As a result, the liquid level in each column is also the same. Now we'll seal the container and add a compressor to pump air inside it. As the air is pumped in, the pressure in the container increases. The pressure on the liquid in this side of the manometer also increases. This causes a difference in the levels of the manometer's two columns. The difference in the levels indicates the amount of pressure in the container above atmospheric pressure. If air is pumped out of the container, a vacuum is created. That is, the pressure in the container is less than atmospheric. Atmospheric pressure pushes on the liquid in this column, and once again, there's a difference in levels. This difference in levels indicates the amount of pressure in the container below atmospheric pressure. That is, it indicates the amount of vacuum in the container. You can't fully understand how pressure is measured unless you're familiar with pressure scales. Three commonly used pressure measuring scales are the absolute scale, the gauge scale, and the vacuum scale. The absolute scale begins at theoretical zero pressure. Theoretical zero is a condition of no pressure and a total absence of matter. On the absolute scale, standard atmospheric pressure is 14.7 pounds per square inch absolute, or PSIA. The faceplates of pressure gauges that use the absolute scale are usually labeled PSIA. Another type of pressure scale is the gauge pressure scale. The gauge scale starts at atmospheric pressure, not at theoretical zero pressure. So atmospheric pressure is given a value of 0. On an instrument that uses the gauge scale, pressure is indicated in pounds per square inch gauge, or PSIG. But sometimes gauge scale values are expressed simply as PSI. It's fairly easy to convert pressure measurements back and forth between the absolute scale and the gauge scale because the basic unit of measurement for each scale is pounds per square inch. We know that 14.7 PSIA equals 0 PSIG. We can use this information in a conversion formula. Absolute pressure equals gauge pressure plus atmospheric pressure. Since absolute pressure equals gauge pressure plus atmospheric pressure, you have to add 20 PSIG to atmospheric pressure, 14.7 PSIA. So the answer is 34.7 PSIA. 20 pounds per square inch gauge equals 34.7 pounds per square inch absolute. To convert from absolute pressure to gauge pressure, you can apply this formula. Pounds per square inch gauge equals pounds per square inch absolute minus atmospheric pressure. The third pressure scale is the vacuum scale. Vacuum is pressure below atmospheric. Like the gauge scale, the vacuum scale uses atmospheric pressure as its starting point. But the vacuum scale moves toward theoretical zero pressure. The closer it gets to theoretical zero, the greater its value. On vacuum gauges, vacuum is often indicated in inches of mercury. This refers to the level of mercury in a vertical column measured from a level representing atmospheric pressure. In other words, if the level of mercury is 8 inches below the level representing atmospheric pressure, then the amount of vacuum is 8 inches of mercury, sometimes abbreviated inches Hg. If theoretical zero pressure, or a condition of perfect vacuum, could be reached, it would have a value of about 30 inches of mercury vacuum. In this topic, we focused on the measurement of pressure. We saw how atmospheric pressure can be measured, and we learned how manometers indicate pressure. We also looked at commonly used pressure scales. Take a minute now to try a few practice questions on this material. Atmospheric pressure is related to height or depth. That is, the pressure of the atmosphere varies with the height of the air above the Earth's surface. For instance, atmospheric pressure at sea level is greater than atmospheric pressure at higher altitudes. If air is pumped out of the container, a vacuum is created. That is, the pressure in the container is less than atmospheric. Atmospheric pressure pushes on the liquid in this column, And once again, there's a difference in levels. To convert from absolute pressure to gauge pressure, you can apply this formula. Pounds per square inch gauge equals pounds per square inch absolute minus atmospheric pressure. This topic explores some of the principles related to flowing liquids. We'll look at flow and flow rate, and we'll see some of the effects of flowing liquids. To view the entire topic at this time, select the View Entire Topic box. To view only a portion of the topic, select the box of your choice. Virtually every system in a process plant contains flowing liquids of one kind or another. Flow occurs when liquid moves. The amount of liquid that is moving and the time it takes to move from one place to another can be measured. These measurements give us a liquid's flow rate. Flow rate can be defined as the amount of liquid flowing past a given point per unit time. To determine flow rate, we'll assume that steady state conditions are in effect. This means that conditions at any given point in a system remain constant with time. In other words, we have to assume that such factors as pressure, temperature, and flow do not change from one second to another. With this in mind, let's take a look at one way to determine the flow rate through a pipe. This illustration represents a section of pipe and a volume of liquid. This dashed line represents a given point in the pipe, as well as the cross-sectional area of the pipe. As you'll see, this area is necessary for our flow rate calculations. When the liquid passes a given point in the pipe, it travels a certain distance in a certain period of time. That is, it has a certain velocity. The flow rate is calculated by multiplying the cross-sectional area of the pipe by the liquid's velocity. In this case, the cross-sectional area is 0.35 square feet, and the velocity is 10 feet per second. So the flow rate is 3.5 cubic feet per second. We used a simple example to introduce the basics of flow rate measurement. In the plant, you'll often find that flow rate is measured in different units, such as gallons per minute or pounds per hour. To understand the effects of flowing liquids, you need to know about a property called head pressure, or simply head. One example of head is the pressure exerted by a column of liquid as a result of its height or level. The amount of pressure exerted also depends on the liquid's density. Denser liquids exert more pressure for a given height than less dense liquids. Another way to explain head is by looking at the relationship between two different pressure measurements, pressure in pounds per square inch and pressure in feet of water. Let's take a look at an example. Atmospheric pressure is 14.7 psi. Atmospheric pressure can support a column of water about 34 feet high. In other words, atmospheric pressure in feet of water is about 34 feet. If we compare atmospheric pressure in psi to atmospheric pressure in feet of water, we find that each foot of water equals 0.433 psi. In other words, a column of water 1 foot high produces a pressure of 0.433 psi. If a pressure gauge were placed at the bottom of this column of water, it would read 0.433 psi. Head is normally expressed in units of feet of liquid, so for water, 1 foot of head is equal to 0.433 psi. Now we're going to turn our attention to some of the effects that flowing liquids can have on head. To help demonstrate these effects, we have a tank of water connected to a simple piping system. This system has 3 standpipes. At the moment, the water's not flowing, so conditions in the system are said to be static. Under static conditions, the levels in the standpipes are the same as the level in the tank. However, when the water is flowing, conditions in the system change. When the water starts flowing, the levels in the standpipes drop. Now they're lower than the level in the tank. So when there's flow, the levels are lower than they were under static conditions. Also notice that the levels in the standpipes are different. To understand why these changes occur, we need to look at 3 properties of liquids: static head, velocity head, and friction head. Static head is related to the level of liquid. Velocity head is the change in static head due to velocity. And friction head is the change in static head due to friction. Friction is a force that opposes motion. Under static conditions, velocity head and friction head are 0 because there is no flow in the system. But when liquids flow, Some of the static head is converted to velocity head. As a result, static head is reduced and the level in the standpipes drops. As velocity increases, static head decreases and the level in the standpipes decreases. As velocity decreases, static head increases and the level in the standpipes increases. To better illustrate the ideas, we'll exaggerate the level changes in the standpipes. Even when there's flow in the system, the liquid in the standpipe still exerts static head. The level in each standpipe is the static head for that pipe. But the difference in the levels is due to the change in static head caused by velocity and friction. The difference in level between the tank and the first standpipe is a result of the velocity of the liquid and the friction between the tank and the first standpipe. Assuming steady-state conditions, the velocity is the same through the horizontal pipe. Therefore, the different levels in the standpipes are a result of the friction in the piping between the standpipes. The decreases in levels represent the decreases in static head caused by friction. The effects of friction increase as the liquid flows through more pipe. Friction in a flowing liquid can come from a variety of factors, including the liquid's viscosity or resistance to flow. Friction can also come from the adhesive forces between the liquid's molecules and the walls of the pipe, and from the turbulence of the flow. In this topic, we examined some of the important properties related to flowing liquids. We looked at the principles behind flow and flow rate, and we saw some of the effects of flowing liquids. Take some time now to answer a couple of practice questions. The flow rate is calculated by multiplying the cross-sectional area of the pipe by the liquid's velocity. Assuming steady-state conditions, the velocity is the same through the horizontal pipe. Therefore, the different levels in the standpipes are a result of the friction in the piping between the standpipes. The decreases in levels represent the decreases in static head caused by friction. The effects of friction increase as the liquid flows through more pipe. Many industrial processes depend on the controlled use of heat. To better understand the vital role that heat plays in the process industries, you need a good grounding in the principles of heat and heat transfer. One of the problems in understanding heat is that you can't see heat directly, but you can see the effects of heat. One effect is seen on this thermometer. The temperature is rising, indicating that heat is being added to the water. Here's another example. This container is filled with air, a gas. Connected to the container are a thermometer and a makeshift manometer, which indicates pressure changes. When we heat the air in the container, there are two main effects. One effect is an increase in temperature. The other is an increase in pressure. As the air's pressure increases, it pushes the liquid in the manometer, changing its level. In the two examples we just saw, the effects of adding heat were obvious, changes in temperature and changes in pressure. The addition of heat caused a change in the properties of the substance. Another possible effect of adding or removing heat is a change in the state or phase of a substance. All substances exist in one of three phases of matter: solid, liquid, or gas. If we heat ice, a solid, of course it melts and changes into water, a liquid. So adding heat has caused the ice to change its state from a solid to a liquid. Then if we heat the water, it boils. So the heat causes the water to change its state from a liquid to a gas, steam. The effects of heat are all related to changes in molecular motion. For example, when heat is added, the motion of the molecules that make up a substance increases. When heat is removed, molecular motion decreases. All solids, liquids, and gases are made up of molecules, and these molecules are constantly moving. Since molecules are always moving, they have kinetic energy. Kinetic energy is the energy of motion. One way to measure kinetic energy is in terms of temperature. Basically, temperature is the degree of hotness or coldness of a substance measured on a scale. As you know, temperature scales usually indicate units of degrees Fahrenheit or degrees centigrade or Celsius. At the molecular level, temperature is a measure of the average molecular kinetic energy of a substance. That is, temperature is an indication of the average molecular motion in a substance. Another way to look at temperature is in terms of intensity. The faster the molecules of a substance move, the more intense the motion is. The greater the intensity, the higher the temperature. Although the molecules in a substance are always moving, some molecules may move faster than others. Boiling water illustrates this principle. With boiling water, some of the water molecules move fast enough to overcome the molecular forces holding them together. When water boils, some of the molecules move fast enough to escape the water as steam. In general, boiling can be defined as the condition at which the molecules of a heated liquid become active enough to escape the liquid. In the case of water, the temperature has to reach 212 degrees Fahrenheit to cause the molecules to move fast enough to leave the water as steam. At this point, we'll turn our attention from temperature to heat. Heat is a form of energy called thermal energy. In a sense, heat is the amount of thermal energy, and temperature is the intensity of the thermal energy. We'll use two beakers of water to illustrate the relationship between temperature and thermal energy. This beaker has only half as much water as this beaker. The temperature in the beaker with less water is 110 degrees Fahrenheit. The temperature in the beaker with more water is 100 degrees Fahrenheit. The beaker with more water contains more thermal energy and therefore more heat than the other beaker. Because there's more water, it takes more heat to raise the temperature of this water than it takes to raise the temperature in the beaker with less water. Although the beaker with less water has less thermal energy, its energy is more intense than the energy in the beaker with more water. The average molecular motion in this beaker is faster, so its temperature is higher. The two units generally used to measure heat are the British Thermal Unit, or BTU, and the calorie. A BTU is the amount of energy needed to raise the temperature of 1 pound of water 1 degree Fahrenheit. A calorie is the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. Heat is a form of energy known as thermal energy. Thermal energy can be either stored in a substance or transferred from one substance to another. There's an important law of energy called the law of energy conservation. This law states that energy can be neither created nor destroyed, only altered in form. Basically, this law means that all energy has to be accounted for. There are a couple of ways the law of energy conservation works. As an example, fuels contain chemical energy. When fuel is burned during combustion, heat is generated. This heat is thermal energy. So the process of burning fuel alters the form of energy from chemical to thermal. Now let's say the heat from combustion is used to heat a process fluid flowing inside furnace tubes. Much of this heat from combustion, or thermal energy, is transferred to the process fluid. Since no furnace operates at 100% efficiency, not all of the heat is transferred to the process fluid. Some of it may go up the stack. Some of it may be absorbed by furnace equipment, but all of it goes somewhere. That is, all of the thermal energy is accounted for, so none of it is destroyed. In this topic, we covered some of the fundamental terms and concepts pertaining to heat. We looked at the effects of heat, and we saw how temperature and thermal energy are related. We also discussed the law of energy conservation. Now's a good time to try a few practice questions. A possible effect of adding or removing heat is a change in the state or phase of a substance. All substances exist in one of three phases of matter: solid, liquid, or gas. Basically, temperature is the degree of hotness or coldness of a substance measured on a scale. As you know, temperature scales usually indicate units of degrees Fahrenheit or degrees centigrade or Celsius. At the molecular level, temperature is a measure of the average molecular kinetic energy of a substance. That is, temperature is an indication of the average molecular motion in a substance. Heat is a form of energy known as thermal energy. Thermal energy can be either stored in a substance or transferred from one substance to another. There's an important law of energy called the law of energy conservation. This law states that energy can be neither created nor destroyed, only altered in form. Basically, this law means that all energy has to be accounted for. A temperature change can be measured or felt. Heat transfer that causes a temperature change is called sensible heat transfer. Heat transfer that does not cause a temperature change is called latent heat transfer. During latent heat transfer, there are changes in molecular energy, but these changes don't result in a temperature change. Instead, they result in a phase change. The three phases or states of matter are solids, liquids, and gases. So, sensible heat results in a temperature change, while latent heat results in a phase change. We'll heat a beaker of ice to demonstrate phase changes and latent heat transfer. We'll also use a graph to show the relationship between temperature and heat. The ice is melting, but at first the temperature stays at 32 degrees Fahrenheit. Latent heat is being absorbed by the ice. The latent heat causes the molecules of ice to overcome the molecular forces holding them together. As a result, the molecules move freely as a liquid. But as yet, there is no temperature change. There's only a phase change from solid to liquid. Now that the ice is melted, the addition of heat does produce a temperature change. At 212 degrees, the water boils into steam, but the temperature stays the same. The water undergoes a phase change, but not a temperature change. At 212 degrees, the latent heat causes the molecules to move fast enough to overcome the molecular forces holding them together. When the molecules absorb enough latent heat, they leave the water as steam. Section B represents sensible heat because from this point to this point, the temperature of the water changes as a result of heat transfer. Section A and Section C represent latent heat transfer because there are no temperature changes in these sections, only phase changes. This horizontal line at 32 degrees represents the latent heat of fusion or melting. The latent heat of fusion is the amount of heat required to melt a substance without a change in temperature or pressure. This point represents ice at 32 degrees, and this point represents water at 32 degrees. The line between these points represents an ice-water mixture. This horizontal line represents the latent heat of vaporization. The latent heat of vaporization is the amount of heat required to vaporize a substance without a change in temperature or pressure. This point represents water at 212 degrees, and this point represents steam at 212 degrees. So the line between these points represents a water-steam mixture. In the example we just saw, heat was added. If heat is removed, the heat transfer line moves in the opposite direction. That is, when heat is removed from steam, the steam starts to condense into water. Under these conditions, heat is removed from steam, and the steam condenses rather than vaporizes. So this line represents the latent heat of condensation. The latent heat of condensation is the amount of heat that has to be removed from a substance to condense it without producing a change in temperature or pressure. Then, when heat is removed from water, there's a sensible heat transfer, and the water temperature drops until it reaches 32 degrees. At that point, any heat removed is latent heat, so the temperature remains at 32 degrees. This line then represents the latent heat of freezing. The latent heat of freezing is the amount of heat that has to be removed from a substance to freeze it without producing a change in temperature or pressure. When a liquid boils, a phase change occurs. A substance changes from a liquid state of matter to a vapor state. The boiling point of a liquid is affected by temperature and pressure. To show how temperature and pressure affect boiling points, we'll use water as an example, but the same basic principles apply for all liquids. The boiling temperature of water is different at different pressures. For example, at atmospheric pressure, water boils at 212 degrees Fahrenheit. But at pressures lower than atmospheric, the boiling temperature decreases. At pressures above atmospheric, the boiling temperature of water increases. To show how temperature, pressure, and heat are related to the boiling point of water, we can construct a graph. The vertical axis represents temperature in degrees Fahrenheit, and the horizontal axis represents heat. We'll use a pound of water as a standard, so the heat's measured in BTUs per pound. A BTU is the amount of heat needed to raise the temperature of 1 pound of water 1 degree Fahrenheit. Atmospheric pressure is 14.7 psia. At atmospheric pressure, water starts boiling at 212 degrees Fahrenheit. On our graph, this is the point at which water first starts boiling at atmospheric pressure. And this is the point at which all the water is boiled into steam. This line represents the amount of heat required to boil all the water. So this line represents the latent heat of vaporization. For 1 pound of water at atmospheric pressure, it takes about 970 BTUs of heat to boil all the water into steam. Now let's take an example in which the pressure is less than atmospheric. At this point, the pressure is 4.9 psia. At this pressure, a pound of water boils at 162 degrees. In addition, the latent heat of vaporization is around 1001 BTUs per pound. So when the pressure is reduced, water boils at a lower temperature. However, it takes more heat to boil all the water into steam than it takes at atmospheric pressure. At lower temperatures, the water molecules move more slowly. As a result, it's harder for them to boil and escape the body of water as steam, so it takes more heat to change the water completely to steam. Now let's look at a pressure that's higher than atmospheric, 114.7 psia. At this pressure, water won't boil until it reaches 338 degrees. Under these conditions, the latent heat of vaporization is about 881 BTUs per pound, which is less than the latent heat of vaporization at atmospheric pressure. At higher temperatures, the water molecules move more quickly than they do at lower temperatures, so it's easier for the molecules to boil and escape the water as steam. In other words, it takes less heat to change the water completely to steam. As the pressure and boiling temperature of water increase, the latent heat of vaporization decreases. There is a point, however, at which the latent heat of vaporization is 0 BTUs per pound. This point occurs at a pressure of 3,206 psia and a boiling temperature of 705 degrees Fahrenheit. This point's called the critical point. Above the critical point, water flashes to steam, but there is no latent heat transfer. Above this point, water exists as a superheated vapor. A superheated vapor is a vapor whose temperature is higher than its boiling temperature. We can draw a curved line that connects these points. This line is called the saturation curve. The points to the left of the critical point represent liquid at the boiling temperature for a given pressure. The points to the right of the critical point represent vapor at the boiling temperature. In this topic, we examined the concept of phase changes. We contrasted latent heat with sensible heat, and we looked at the effects of temperature and pressure on the boiling point of water. Let's stop for a moment so you can answer a few practice questions. A temperature change can be measured or felt. Heat transfer that causes a temperature change is called sensible heat transfer. Heat transfer that does not cause a temperature change is called latent heat transfer. At higher temperatures, the water molecules move more quickly than they do at lower temperatures, so it's easier for the molecules to boil and escape the water as steam. In other words, it takes less heat to change the water completely to steam. As the pressure and boiling temperature of water increase, the latent heat of vaporization decreases. Look around just about any process plant. You're likely to find boilers, furnaces, and many other types of heat exchangers. It's a diverse assortment of equipment, but all of it depends on heat transfer in one way or another. One way to define heat transfer is as thermal energy that's moving from one substance to another, or from one part of an object to another. This movement is a result of a temperature difference. We can show how temperature differences affect heat transfer with a simple demonstration. The ice cubes have a temperature of 32 degrees Fahrenheit. They're in water that's at room temperature, about 72 degrees Fahrenheit. Because of this temperature difference, heat transfer occurs. Heat naturally transfers from an area or substance of higher temperature to an area or substance of lower temperature. So heat transfers from the water to the ice. The heat from the water is absorbed by the ice, raising its temperature and causing it to melt. As heat is transferred, the water cools, so its temperature decreases. Here's another way to see what's going on. The molecules in the higher temperature water are moving relatively quickly. They have a relatively high average kinetic energy. The molecules in the lower temperature ice are moving more slowly. They have a relatively low average kinetic energy. The water molecules collide with the ice molecules. As the molecules collide, energy is transferred from the water molecules to the ice molecules. As a result, the water molecules slow down and the ice molecules speed up. This transfer of molecular energy between the water and the ice is an example of heat transfer. We can plot the temperatures of the ice and water on a temperature-time graph. We've speeded up the action to save time. As the water transfers its heat to the ice melts and the temperature of the water decreases. The rate of the temperature decrease slows down as the water temperature approaches the temperature of the ice, 32 degrees. This indicates that the rate of heat transfer is slowing down. As the ice continues to melt, the ice-water mixture approaches thermal equilibrium. Thermal equilibrium is the condition in which the temperatures of two substances are equalized. When two substances are at thermal equilibrium, no heat transfer takes place. Without a temperature difference, no heat can be transferred. A temperature difference is sometimes called the driving force of heat transfer. A greater temperature difference between substances produces a higher rate of heat transfer. A smaller temperature difference produces a lower rate of heat transfer. Different substances require different amounts of heat to change their temperature. The amount of heat that has to be added to or removed from a substance to change its temperature is called its thermal capacity, or specific heat. More precisely, specific heat is the amount of heat needed to raise the temperature of 1 pound of a substance 1 degree Fahrenheit. Amounts of heat are often expressed in British thermal units, or BTUs. 1 BTU is the amount of heat needed to raise the temperature of 1 pound of water 1 degree Fahrenheit. Water is given a specific heat value of 1. In other words, it takes 1 BTU to raise the temperature of 1 pound of water 1 degree Fahrenheit. Water is treated as a standard that other substances are compared to. For example, the specific heat of ice is 0.5, so it takes half as much heat to raise the temperature of ice as it does to raise the temperature of water. Air has a specific heat of 0.25, and steel has a specific heat of 0.115. Substances with lower specific heats require less heat to raise their temperature than substances with higher specific heat. The amount of heat that's transferred into or out of a plant process is affected by many factors, and we can't cover them all here. But 3 of the primary factors are the temperature change the substance undergoes, the amount of the substance, and the type of substance involved. These factors can be related in terms of a heat transfer formula. In this formula, the amount of heat transferred into or out of a substance is expressed in BTUs. The amount of heat transferred equals m, the mass or amount of substance involved, times its specific heat, which relates to the type of substance involved, times the difference between the final temperature of the substance, Tf, and the initial temperature, Ti. The difference between the final temperature and the initial temperature represents the temperature change. If the final temperature is greater than the initial temperature, heat was added to the substance. If the final temperature is less than the initial temperature, heat was removed. If any of these factors increases, the amount of heat transferred into or out of the substance also increases. In other words, if you increase mass, specific heat, or temperature change, the amount of heat transferred into or out of the substance also increases. If you decrease mass, specific heat, or temperature change, the amount of heat transferred into or out of the substance also decreases. This should give you a basic idea of how these factors affect heat transfer. In this topic, we saw how temperature differences and heat transfer are related, and we introduced the concept of specific heat. We also saw how the mass, specific heat, and temperature change of a substance are related in a heat transfer formula. Let's take a minute now to do some practice questions. Thermal equilibrium is the condition in which the temperatures of two substances are equalized. When two substances are at thermal equilibrium, no heat transfer takes place. Without a temperature difference, no heat can be transferred. Different substances require different amounts of heat to change their temperature. The amount of heat that has to be added to or removed from a substance to change its temperature is called its thermal capacity, or specific heat. In this formula, the amount of heat transferred into or out of a substance is expressed in BTUs. The amount of heat transferred equals m, the mass or amount of substance involved, times its specific heat, which relates to the type of substance involved, times the difference between the final temperature of the substance, Tf, and the initial temperature, Ti. The difference between the final temperature and the initial temperature represents the temperature change. If the final temperature is greater than the initial temperature, heat was added to the substance. If the final temperature is less than the initial temperature, heat was removed. One way that heat's transferred is by conduction. It's the primary mode of heat transfer within a solid or between solids in contact. For example, conduction is the mode of heat transfer through metal tubes in a heat exchanger. If the outside wall of a tube is heated, the heat transfers by conduction to the inside wall. The speed or rate at which heat is transferred by conduction depends on four main factors: the thickness of the material, the temperature difference across the material, the surface area over which the heat is applied, and the material's thermal conductivity. In the case of a tube, thickness refers to the distance from the outside wall to the inside wall. As the thickness increases, the rate of conduction heat transfer through the wall decreases because the distance that the heat must travel is increased. It takes longer for the heat to travel the extra distance. As thickness decreases, the rate of heat transfer increases. The heat has less distance to travel. Another factor is the temperature difference across the tube wall. For example, let's say that the outside wall temperature is 200 degrees and the inside wall temperature is 150 degrees. The temperature difference across the tube wall is 50 degrees. The greater the temperature difference, the greater the rate of conduction heat transfer. So a temperature difference of 50 degrees will produce a greater rate of heat transfer than a temperature difference of 25 degrees. The amount of surface area available for heat transfer also affects conduction. Surface area is normally expressed in square feet, and the greater the surface area, the greater the rate of conduction heat transfer. A larger surface transfers heat at a greater rate than a smaller surface. Thermal conductivity is another factor that affects conduction heat transfer. Basically, thermal conductivity is a material's ability to transfer heat. This ability varies depending on the material. For example, dense materials, like metals, are good conductors of heat. They have high thermal conductivity. Less dense materials, like styrofoam, are poor conductors. They have low thermal conductivity. Piping insulation is a good example of how thermal conductivity and material thickness affect heat transfer. Insulation reduces heat loss by reducing the rate of heat transfer to a minimum. Insulating materials have relatively low thermal conductivities. Also, the thicker the insulation around a pipe, the less heat will be transferred through the insulation. The temperature difference between the fluid inside the piping and the outside air may be several hundred degrees, but the insulation keeps the rate of heat transfer between the fluid and the air very low. Convection is the primary mode of heat transfer within or between fluids. Fluids are liquids and gases. To demonstrate convection, we'll heat a beaker of water on a hot plate and add some dye. As the water in the bottom of the beaker warms up, it rises and mixes with the cooler water. The movement of fluids is a distinctive characteristic of convection. Heat is transferred as the fluids move and mix. Convection heat transfer relates to how fluids move. Fluid movement is often divided into two categories: natural convection and forced convection. The type of convection depends on what produces the fluid movement. We've set up a loop to show the principle of natural convection. When we heat one side of the loop, the fluid in that side gets lighter, that is, less dense. The warmer and lighter fluid rises. It's replaced by cooler, denser, and therefore heavier fluid coming in behind it. The difference in density between the warmer water and the cooler water starts the flow in the loop. When more heat's added, the temperature difference between the warmest and coolest liquid increases, and the flow rate increases. If the temperature difference decreases, the flow rate decreases. The flow of liquid causes heat to be transferred by convection throughout the system. Instead of using natural convection, many systems use forced convection, which usually involves a mechanical device like a pump or a fan which circulates the fluid through the system. Convection heat transfer occurs within or between fluids. Heat transfer between fluids often occurs when they're separated by a solid boundary. This represents a solid wall with a hot fluid on one side and a cold fluid on the other. Heat transfers by convection from the hot fluid to the wall. Heat then transfers by conduction through the wall. From there, heat is transferred by convection throughout the cooler fluid. One factor affecting the rate of heat transfer is the temperature difference between the fluids. A greater temperature difference increases the rate of heat transfer. A smaller temperature difference decreases the rate of heat transfer. Heat transfer is also affected by the rates at which the fluids are flowing. For example, if the temperature difference between the two fluids remains constant, but the flow rate of one of the fluids increases, the rate of heat transfer will also increase. More fluid flows past the heat transfer surface, so there is more fluid available to deliver or receive heat. One mode of heat transfer is radiation. With radiation, heat is transferred by electromagnetic waves. All matter gives off energy in the form of electromagnetic waves. A major source of radiant energy is the sun, which transfers heat through relatively empty space. Some of the waves are absorbed by the Earth as heat that warms the Earth. We can demonstrate radiant heat transfer by placing two thermometers close together. One's in direct sunlight, the other's in the shade. Both thermometers are surrounded by the same air, but, as you'd expect, the thermometer in the sunlight reads higher than the one in the shade. That's because the thermometer in the sun is receiving radiant heat from the sun. One factor that influences radiant heating is the color of the substance that's absorbing heat. In plants, for example, most insulated piping is covered with shiny or light-colored materials. These materials reflect most of the radiant energy that contacts them, so they absorb little radiant heat. This helps retain the radiant heat inside the pipe. As a result, the amount of radiant heat lost through the piping and insulation is minimized. In this topic, we looked at the three modes of heat transfer: conduction, convection, and radiation. We discussed the underlying principles of each mode, and we saw how they're applied in plant processes. Let's take a moment now to try a few practice questions. One way that heat's transferred is by conduction. It's the primary mode of heat transfer within a solid or between solids in contact. For example, conduction is the mode of heat transfer through metal tubes in a heat exchanger. If the outside wall of a tube is heated, the heat transfers by conduction to the inside wall. One factor that influences radiant heating is the color of the substance that's absorbing heat. In plants, for example, most insulated piping is covered with shiny or light-colored materials. These materials reflect most of the radiant energy that contacts them, so they absorb little radiant heat. There are many different types of heat exchangers. These include coolers, heaters, condensers, and waste heat recovery units, to name a few. Despite this variety, most heat exchangers have several aspects in common. There's usually a hot fluid and a cool fluid, and both fluids flow through the heat exchanger. There's also a surface through which heat transfer takes place. A shell and tube heat exchanger is one of the most commonly used types in a plant. The shell is simply the outer casing of the heat exchanger. Inside the shell, there's a bundle of tubes. The tubes carry one of the fluids and act as a boundary to separate the fluids in the heat exchanger. The tube walls provide a surface area for the heat transfer between the two fluids. Tube sheets support the tubes and help form the heads. The heads are the ends of the heat exchanger. the fluid that flows through the tubes enters and exits through the heads. In this heat exchanger, the hotter fluid flows through the tubes, and the cooler fluid flows around the tubes. Fluid in the tubes exchanges heat with fluid around the tubes. As the two fluids flow through the heat exchanger, heat transfers from the hotter fluid to the cooler fluid. As a result, the hotter fluid is cooled and the cooler fluid is heated. In some heat exchangers, the fluids flow in opposite directions to this. That is, the cooler fluid flows through the tubes and the hotter fluid flows around the tube. The rate of heat transfer is generally controlled by adjusting the flow rates of one or both fluids. This is usually accomplished by adjusting flow control valves. A common type of heat exchanger is a shell and tube lubricating oil cooler, or lube oil cooler. Like all heat exchangers, lube oil coolers involve a hot fluid and a cool fluid. The hot fluid is the lubricating oil, and the cool fluid is usually water. There's a lot of operating machinery in a plant that needs proper lubrication. The purpose of a lube oil cooler is to maintain the temperature of the lube oil within a certain range to keep it from overheating. Overheated oil may not lubricate equipment properly. The proper lube oil temperature can be maintained by controlling the flow of water through the cooler. Many factors can lead to abnormal conditions in a heat exchanger. Some common problems are scale, corrosion, tube leakage, and tube blockage. Scale is a buildup of solid impurities on the inside of a tube wall. Scale acts as an insulator, reducing the tube's ability to transfer heat. Another problem, corrosion, can also form on tube surfaces and act as an insulating layer. This, too, can lead to heat transfer problems. In addition, corrosion can eat away and weaken tube metal, which may lead to tube leakage. If a tube leaks, the heat transfer process is affected. But an even more serious problem is the contamination of fluids flowing through the heat exchanger. When leaks occur, the heat exchanger is usually shut down for inspection and repair. If only a few tubes are leaking, the tubes could be plugged and the heat exchanger put back into service, but at reduced efficiency. If there are a lot of tubes leaking, more extensive repair work may need to be done. Another problem is tube blockage. It may be caused by a buildup of aquatic life, microorganisms, or debris in the tubes or on the tube sheet. If tube blockage occurs, the fluid has fewer tubes to flow through. This reduces the area available for heat transfer within the heat exchanger, so the amount of heat transfer decreases. If too many tubes are blocked, flow through the heat exchanger is reduced. Under these conditions, it may be possible to increase the flow rate through the heat exchanger to maintain the proper heat transfer. Often, though, the heat exchanger will have to be shut down for cleaning to remove the blockage. In some cases, heat exchangers are backwashed. The liquid in the tubes is sent through in the opposite direction to dislodge debris that could be impeding flow. In this topic, we introduced some of the fundamentals related to heat exchanger operation. We looked at shell and tube heat exchangers, and we saw some common heat exchanger problems. Take a minute now to try a few practice questions on this material. Inside the shell, there's a bundle of tubes. The tubes carry one of the fluids and act as a boundary to separate the fluids in the heat exchanger. The tube walls provide a surface area for the heat transfer between the two fluids. Scale is a buildup of solid impurities on the inside of a tube wall. Scale acts as an insulator, reducing the tube's ability to transfer heat. Convection heat transfer relates to how fluids move. Fluid movement is often divided into two categories: natural convection and forced convection. The type of convection depends on what produces the fluid movement. We've set up a loop to show the principle of natural convection. When we heat one side of the loop, the fluid in that side gets lighter, that is, less dense. The warmer and lighter fluid rises. It's replaced by cooler, denser, and therefore heavier fluid coming in behind it. The difference in density between the warmer water and the cooler water starts the flow in the loop. During the operation of a fluid system, process variables such as pressure, flow, level, and temperature may remain relatively constant over a period of time. Under these circumstances, the system is said to operate under steady-state conditions. However, operating changes and process disturbances are a common part of system operation. And when changes occur, process control systems may make adjustments that result in a new set of steady-state conditions. The period of operation that occurs between one set of steady-state conditions and another is known as dynamic operation. Process disturbances and operating changes are a common part of fluid system operation. The way that a system responds to changes can depend on different factors or characteristics. Two important characteristics that can affect a system's response to changes are resistance and capacitance. Resistance can be thought of as an opposition to flow. Capacitance can be thought of as the ability to store energy. While these terms are commonly used in discussing electrical circuits, they can also be applied to other processes and systems. For example, in this simplified liquid system, a container serves as a reservoir for the liquid. The energy for the system is the liquid's head, that is, the pressure caused by the depth of the liquid. The resistance in the system is caused primarily by a valve that opposes the flow of liquid from the container. When the valve is closed, the resistance is high and there's no flow. But if the valve is opened, the resistance or opposition to flow decreases and liquid flows from the container. This system's capacitance or ability to store energy is determined by the size of the container. The larger the container, the greater the ability to store energy and the greater the capacitance. These same basic characteristics can also be applied to gas or vapor systems. For example, in this simplified gas system, the resistance is caused primarily by a valve that opposes the flow of gas from a pressurized cylinder. The capacitance, or the ability of the system to store energy, depends on the storage capacity of the cylinder. Now, in a thermal process, that is, one involving heat, resistance and capacitance may be somewhat different. Here, a flame is used to heat a beaker of liquid. In this arrangement, the wall of the beaker represents the resistance, since it resists the transfer of heat from the flame to the liquid. The amount of heat or thermal energy that the liquid is able to store represents the capacitance of the system. Regardless of the form that they take, resistance and capacitance can greatly affect a system's response to operating changes. Changes that occur in a fluid system typically do not produce an immediate visible effect. In fact, it can take anywhere from a few seconds to several hours for a change in one part of a system to produce a noticeable change in another part of the system. The reason for this time delay has to do with the physical characteristics of the system. For example, in this simplified liquid system, a valve offers resistance to the flow of liquid from a container. The size of the container determines the system's capacitance. With the valve closed, there's no flow through the system. Let's see what happens when the valve is opened. We'll plot the effects of opening the valve on this graph. The vertical axis of the graph represents flow, and the horizontal axis represents time. When the valve is opened, the flow of liquid from the container increases rapidly at first, then levels off at its maximum value. The curve that's formed on the graph is often referred to as a dynamic response curve. It illustrates a basic fact about a system's response to operating changes. The response is gradual, not immediate. Other processes exhibit similar responses to operating changes. For example, in this heat exchanger, steam is used to heat water for a process. The steam flows through coils in the water heater, while the water flows around the coils. At the moment, the temperature of the steam entering the heater is 400 degrees Fahrenheit, and the temperature of the water leaving the heater is 200 degrees Fahrenheit. Now, suppose the temperature of the steam suddenly rises to 500 degrees. Even though the steam temperature increased suddenly, the water temperature will remain unchanged briefly, then increase slowly. It's easier to see why the water temperature changes this way by plotting the temperature changes on a graph. On the graph, the vertical axis represents temperature, and the horizontal axis represents time. When we plot the steam temperature, we see the sudden increase from 400 degrees to 500 degrees. This type of disturbance is commonly called a step input. But when we plot the water temperature, we see that there's a delay between when the steam temperature increased and when the water temperature first started to rise. This delay is called dead time. It can be thought of as the amount of time required to transfer energy from one point to another. We also see that once the water temperature started to rise, it rose gradually, not suddenly. That's why the shape of the water temperature curve is similar to the dynamic response curve that we saw earlier. The total amount of time from when the steam temperature changed until the water temperature reached its maximum amount of change is called lag. Lag is caused by the combined effects of dead time and other process characteristics, such as resistance and capacitance. In this process, the transfer of heat from the steam to the water was delayed because of the resistance to heat transfer in the steam coils and because of the water's capacitance, or the ability of the water to store heat. While resistance and capacitance are two of the major factors that affect a system's response to operating changes, they aren't the only factors. Another common one is related to distance. For instance, in the water heater example, the water temperature was measured just downstream from the heater. But if the temperature were measured farther away, it would take longer for a change in water temperature to be detected. On the graph showing steam and water temperatures, the added distance from the heater to the indicator would show up as a longer time delay between the increase in steam temperature and the increase in water temperature. The greater the distance between the heater and the indicator, the greater the time delay. Physical characteristics such as distance, capacitance, and resistance can all delay a system's response to operating changes. For that reason, you need to give a system time to respond to changes before you try to determine whether or not the system is operating normally. Complex systems can take time to respond and settle out when changes occur. Knowing how physical characteristics can affect a system can help you determine if process variables are changing as they should. Also, since changing conditions at one point in a system can affect other parts of the system, you need to be familiar with the location and operating characteristics of system components. In this topic, we focused on changes that occur in a fluid system during dynamic operation. We identified several different factors that can affect a system's response to operating changes, and we examined the effects that those factors can have on a system. Now let's try some practice questions that relate to this material. Now, in a thermal process, that is, one involving heat, resistance and capacitance may be somewhat different. Here, a flame is used to heat a beaker of liquid. In this arrangement, the wall of the beaker represents the resistance, since it resists the transfer of heat from the flame to the liquid. In this heat exchanger, a sudden increase in steam temperature will cause the water temperature to increase slowly. It's easier to see why the water temperature changes this way by plotting the temperature changes on a graph. On the graph, the vertical axis represents temperature, and the horizontal axis represents time. When we plot the steam temperature, we see the sudden increase from 400 degrees to 500 degrees. This type of disturbance is commonly called a step input. But when we plot the water temperature, we see that there's a delay between when the steam temperature increased and when the water temperature first started to rise. This delay is called dead time. It can be thought of as the amount of time required to transfer energy from one point to another. We also see that once the water temperature started to rise, it rose gradually, not suddenly. In a plant, many different variables are monitored by process instrumentation. One of the most commonly monitored variables is pressure. While pressure itself is a key process variable, it's also closely associated with other process variables such as flow. Pressure can be measured using a lot of different devices. We'll focus on two pressure elements that are commonly found in pressure measuring instruments: a board-on-tube and a bellows. Both of these devices convert changes in pressure to mechanical motion. A board-on-tube pressure element is basically a curved hollow tube. One end of the tube is closed. It's connected to a mechanical linkage, which in this case is connected to a pointer that's used together with a scale. The other end of the tube is open so that the pressure from the process is exerted inside of the tube. When pressure is applied to the board-on-tube, the tube tries to straighten out. The movement of the tube is transferred through the mechanical linkage to the pointer. When the pressure being applied to the tube decreases, the tube curls up. This causes the mechanical linkage in the pointer to move in the opposite direction. Another pressure element that's used in industry is a bellows. A bellows is basically a movable accordion-shaped tube. In this arrangement, one end of the bellows is connected to a pressure source, while the other end is connected to a mechanical linkage that's used to move a pointer up and down a scale. When pressure is applied, the bellows expands. As the bellows moves, the mechanical linkage moves the pointer as well. When pressure is removed, the bellows contracts, and the pointer moves in the opposite direction. In general, bellows elements are very sensitive pressure detectors. Also, they can be set up to measure pressure in different ways. For example, the bellows in this arrangement is designed to measure pressure changes that occur inside of the bellows. The bellows is connected at the bottom of a chamber to a pressure source, so any change in pressure acts on the inside of the bellows. Here's a different arrangement. In this case, the bellows is attached at the top of the chamber. The bottom of the bellows is sealed, so the pressure that's applied at the bottom of the chamber acts on the outside of the bellows. A bellows can also be set up to measure the difference between two pressures. Here, the bellows measures the difference between the pressures that are applied at the bottom of the chamber and the top of the chamber. In a fluid system, it's often necessary to determine how much fluid is used, moved, or produced. To provide this information, different types of flow measurement devices are used. Not all flow measurement devices work the same way. Some measure the actual amount of fluid that passes through them. We'll call them direct flow measurement devices. Others measure process conditions that are related to flow, such as pressure. Then they convert those measurements to flow indications. We'll call them indirect flow measurement devices. This nutating disc meter is one device that measures flow directly. It gets its name from the action of a disc located inside the meter. The word nutate means to wobble or roll about an axis of rotation. During operation, fluid enters the meter through the inlet. The fluid flow causes the disc to rotate much like a slowly spinning top. As the disc rotates, specific amounts of fluid are trapped above and below the disc. If a change in the process causes the flow rate to increase, the disc rotates faster, but the same amount of fluid is passed along with each rotation. A counter mechanism counts each rotation of the disc to keep track of how much fluid is passed through the meter. While direct flow measurement devices measure the actual amount of fluid that flows through them, some indirect flow measurement devices rely on some type of energy conversion to indicate flow. One of the most common devices used for indirect flow measurement is an orifice plate. An orifice plate is basically a plate with a hole or orifice in it that's used to restrict the flow of fluid through a pipe. More specifically, the orifice plate causes an energy conversion to take place. As fluid flows through the opening in the orifice plate, its pressure decreases and its velocity increases. The conversion of pressure to velocity causes the pressure on the downstream side of the plate to fall below the pressure on the upstream side. A device such as a differential pressure, or DP cell, measures the difference between the two pressures and provides a corresponding flow rate signal. If the flow rate through the opening in the orifice plate increases, the difference between the two pressures increases as well, and the DP cell provides a signal representing a higher flow rate. By converting energy from one form to another, an orifice plate creates a differential pressure, and enables the flow rate of a fluid to be determined indirectly. Accurate level measurement helps ensure that proper amounts of materials are maintained in plant systems. One device that's sometimes used to measure level in fluid systems is a displacer. A displacer operates on the principle of buoyancy. This principle states that when a body is immersed in a fluid, it's lifted or buoyed up by a force that's equal to the weight of the displaced fluid. To see how the principle of buoyancy applies to a displacer, we'll use this illustration of a displacer attached to a container of liquid. Liquid levels equalize in containers that are connected together, so the level inside the displacer's chamber stays the same as the level in the container. A weight hangs in the chamber and is connected through a linkage to a transmitter. The higher the level of the liquid in the tank and the chamber, the more liquid is displaced by the weight, and the greater the buoyant force. The increase in buoyant force causes the weight to rise slightly in the chamber. The linkage transfers the movement of the weight to the transmitter, which in turn transmits a signal representing the level to an indicator or a controller. Another way to measure level is to use a device that measures head. Head can be thought of as the pressure exerted by a liquid as a result of its height or depth. For example, the pressure exerted on the gauge mounted near the bottom of this container depends on the depth of the liquid. Now, the density of a static liquid will also affect pressure, but in this case, the density doesn't change. If the level of the liquid increases, the pressure exerted on the gauge increases as well, and the gauge converts that pressure to an indication of level. Temperature is a key process variable that's commonly monitored in plants. Temperature can be measured using different types of temperature measuring devices. One of the most common temperature measuring devices is a thermometer, such as this liquid in glass or liquid-filled thermometer. It consists of a glass tube which contains a liquid and a calibrated scale. This particular scale is in units of degrees Fahrenheit, but other scales, such as degrees Celsius, are commonly used. A liquid-filled thermometer operates on the basis that most liquids expand when they're heated and contract when they're cooled. Increases in temperature cause the liquid to expand and move up the tube. Decreases in temperature cause the liquid to contract and move down the tube. The level of the liquid in the tube indicates the temperature of the substance being measured. Another device that's often used to measure temperature in industrial applications is a thermocouple. A thermocouple consists of two wires made of dissimilar metals, which are joined at one end so that they produce an electrical voltage. The other ends of the wires complete a circuit to a measuring device with an indicator. When the temperature sensed by the joined ends changes, the voltage generated by the wires changes as well. That voltage is detected by the measuring device and displayed as a temperature indication. In this topic, we focused on the measurement of four common process variables: pressure, flow, level, and temperature. We looked at several devices commonly used to measure these variables. Now let's try some practice questions that relate to this material. Another pressure element that's used in industry is a bellows. A bellows is basically a movable accordion-shaped tube. In this arrangement, one end of the bellows is connected to a pressure source, while the other end is connected to a mechanical linkage that's used to move a pointer up and down a scale. When pressure is applied, the bellows expands. As the bellows moves, the mechanical linkage moves the pointer as well. An orifice plate is a plate with a hole in it that's used to restrict fluid flow through a pipe so that flow can be measured indirectly. In this arrangement, a gauge that's mounted near the bottom of a container provides a level indication based on the liquid's head. That is, the pressure exerted by the liquid as a result of its height or depth. A thermocouple consists of two wires made of dissimilar metals, which are joined at one end so that they produce an electrical voltage. The other ends of the wires complete a circuit to a measuring device with an indicator. When the temperature sensed by the joined ends changes, the voltage generated by the wires changes as well. That voltage is detected by the measuring device and displayed as a temperature indication. In this heat exchanger, steam is used to heat water for a process. If the temperature of the steam entering the heat exchanger suddenly increases, what will happen to the temperature of the water leaving the heat exchanger? In this arrangement, a single valve is used to control the flow of liquid from a container. Suppose the valve is moved from the fully closed position to the fully open position. Many plant systems and processes involve the handling and interaction of solids and liquids. To work safely and productively, operators need to be familiar with the principles related to solids and liquids. Matter is generally considered to be anything that has weight and takes up space. Matter can be visible, like steel and water, or invisible, like air. Matter can exist in three forms: solid, liquid, and gas. Solids have definite shapes and definite volumes. The volume is the amount of space that matter occupies. Liquids have definite volumes, but the shape of a liquid depends on the shape of its container. Gases do not have definite shapes or definite volumes. The shapes and volumes of gases change to match the shapes and volumes of their containers. The terms solid, liquid, and gas refer to the state or phase of a substance. Most substances can exist in any of the three states. For example, water is usually a liquid, but it can also exist as a solid in the form of ice or as a gas in the form of steam. The state in which a substance exists is influenced by temperature and pressure. For instance, to change water from a liquid to a gas, there have to be changes in its temperature, pressure, or both. Each state of matter has its own unique properties, but before we look at them, let's see how matter is structured in general. All matter is made up of very small particles called atoms. Atoms are made up of even smaller particles. These particles include electrons that revolve around a nucleus. The electrons are negatively charged particles. The nucleus is made up of protons, which are positively charged, and neutrons. Neutrons do not have a charge. When atoms combine with other atoms, they form molecules. A molecule is the smallest particle of a substance that retains all the properties of that substance. For example, one molecule of common table salt has all the properties of salt. A salt molecule contains one atom of sodium, Na, and one atom of chlorine, Cl. One molecule of water has all the properties of water. A water molecule contains two molecules of hydrogen and one of oxygen. The way molecules fit together is referred to as molecular structure. Molecular structure is influenced by temperature and pressure, which help determine whether a substance is a solid, liquid, or gas. Molecular structure is also influenced by cohesive forces that exist between molecules. Cohesive forces attract like molecules. For example, water forms droplets partially because of the cohesive forces that hold water molecules together. In addition to cohesive forces, there are also adhesive forces, which attract unlike molecules. Water droplets will wet the sides of a container because of the adhesive forces between the water molecules and the molecules of the container. That gives you some background on matter and molecular structure. Let's take a closer look now at the three phases of matter. We'll start with solids. As we've seen, solids have a definite shape and a definite volume. Solids retain their shape and volume because of their molecular structure. Each sphere represents a molecule. The molecules fit together in an arrangement called a lattice structure or crystal structure. This one has an orderly geometric shape. Another characteristic of solids is that the molecules are packed closely together compared to the molecules of liquids or gases. There's not as much space between the molecules. The close packing in a solid is a result of the strong cohesive forces between the molecules. The attraction of the molecules holds them together and gives a solid its rigidity and firmness. This crystal represents common table salt. Each sphere is one molecule of salt. If more salt molecules are added, they combine along the edges of the cubic structure, forming a larger salt crystal. The structures of solids range from simple to complex. The exact molecular structure of a solid determines many of its strength and hardness characteristics. Although you can't tell it with the naked eye, the molecules in solids do move. Because of the strong cohesive forces between the molecules, the movement is limited to vibration and spin. In other words, the molecules in solids basically move in place. The molecular structure of liquids is different from that of solids. The molecules of liquids are spaced farther apart because the cohesive forces of liquids are weaker than those of solids. As a result, liquid molecules move more freely than solid molecules. The ability of liquid molecules to move over each other is what enables liquids to flow. Another characteristic of liquids is that they assume the shapes of their containers. Also, the cohesive forces of liquid molecules are strong enough to hold the liquid together and give it a definite volume. Compared to solids and liquids, gases are made of molecules that are spaced much farther apart. There are practically no cohesive forces between gas molecules, and there is a lot of empty space between the molecules. So, gas molecules move even more freely than liquid molecules. Also, due to the lack of cohesive forces, gases do not maintain definite shapes or volume. In this topic, we looked at the three forms of matter, and we examined the molecular structure of each form. We also looked at atoms, the building blocks of all matter, and learned how they're structured as well. At this point, take a minute to answer a couple of practice questions on this material. Compared to solids and liquids, gases are made of molecules that are spaced much farther apart. There are practically no cohesive forces between gas molecules, and there is a lot of empty space between the molecules. So, gas molecules move even more freely than liquid molecules. Liquids have definite volumes, but the shape of a liquid depends on the shape of its container. Mass is the amount of matter possessed by a body. The measurement of mass is typically expressed as weight. So, the mass of a solid object can be found by weighing it with a scale. The weight of a solid object in pounds is the same as the mass of the object in pounds. In this case, the mass of the object is 2 pounds. The density of an object is related to its mass. Density is the amount of mass in a given volume of a substance. That is, the density is mass per unit volume. As an example, gold has a density of 1,205 pounds per cubic foot. Working out the math, we find that a 1-pound cube of gold has a volume of about 1.43 cubic inches, which is just over 1 inch on a side. In contrast, aluminum is much less dense than gold. Aluminum has a density of only 168.5 pounds per cubic foot. This means that a 1-pound cube of aluminum has a volume of 10.26 cubic inches. At this volume, the cube is just over 2 inches on a side. Density is a property that can help identify different substances that are similar in appearance. Density is also one of the properties that helps distinguish solids, liquids, and gases. In general, solids have a higher density than liquids or gases. A condition relating to solids is stress. Stress is the result of applied forces. These forces can alter the molecular structure of a solid, causing it to change shape. There are basically 5 types of stress that can affect solids: tension, compression, bending, twisting, and shearing. In a way, tension and compression are opposites. Tension occurs when external forces try to pull a body apart. And compression occurs when external forces push on a body. That is, try to push the particles of a body together. Bending and twisting forces are fairly self-explanatory. A bending force tries to bend a body, whereas a twisting force tries to twist a body. Shearing is a stress in which forces are applied parallel to each other and in opposite directions. In other words, shearing tends to make parts of a body slide across each other. These 2 blocks demonstrate the principle, but in reality, a single block would be sheared in 2. Stress works in various ways in plant equipment. For example, compression and tension occur in systems that operate under pressure. Changes in pressure can produce tension and compression. Forces act to pull objects apart or push them together. Bending may occur with a beam that supports a load. The weight causes the beam to bend slightly, but if the load is too heavy, the weight could cause the beam to fail. Twisting stress is predominant in rotating machinery, like the shaft assemblies in motors and pumps. If the twisting stress is greater than the design limits of the shaft assembly, the equipment could be damaged. The weight of a girder applies shearing stress on the bolts. If the stress is great enough, the bolts can be literally sheared in two. All plant equipment is designed to operate under some stress, but it has to be operated within its design stress limits. If it's not, it's subject to damage. A property of many solids is their elasticity. That is, their ability to return to their original shape after being deformed by stress. Piping systems provide a good example of elasticity. Because they're subject to temperature and pressure changes, piping system components often expand and contract. If the pressure of fluid in a pipe increases, the pipe expands, because the increased pressure exerts a force on the inner surface. We've exaggerated the expansion, but even a small amount causes stress. When the pressure is removed, the pipe contracts or returns to its original shape because of its elasticity. If a pipe is overpressurized, the excessive stress may push the elasticity of the pipe beyond its limits. If the stress is great enough, the pipe could rupture. Solids that are highly elastic will generally yield to the deforming forces of stress. Steel, for example, can withstand a lot of stress before it loses its elastic properties. That is, before it reaches its elastic limit. The elastic limit is the point at which the force applied to a solid exceeds the ability of the solid to return to its original shape. It's the point at which the solid will remain deformed. In a general sense, temperature is the relative hotness or coldness of a substance. But at the molecular level, temperature is a measure of the average molecular kinetic energy of a substance. Kinetic energy is the energy of an object in motion, so temperature is related to molecular motion. In a solid, the molecules vibrate within their rigid structure. The temperature of the solid is determined by the amount of vibration. If heat is applied to a solid, molecular motion increases. If enough heat is applied, the molecular motion can become great enough to overcome the cohesive forces holding the molecules together. The bonds between the molecules of the solid will begin to break down so that the molecules can move more freely. It's at this point that the solid begins to melt into a liquid. Using a common example, when heat is applied to ice, the heat causes the molecular structure of the ice to break down. As a result, the ice melts. In plants, if machinery overheats, the molecular structure of the machine's material may be damaged or weakened. The equipment may fail, or it may continue to operate for a while with no apparent signs of damage. But the operating life of an overheated machine is shortened, so it's important to operate plant equipment within design limits. In this topic, we looked at some of the important physical properties and conditions related to solids. These include mass, density, stress, and elasticity. We also saw how solids are affected by temperature. Now's a good time to try a few practice questions. Mass is the amount of matter possessed by a body. The measurement of mass is typically expressed as weight. A property of many solids is their elasticity. That is, their ability to return to their original shape after being deformed by stress. In a general sense, temperature is the relative hotness or coldness of a substance. But at the molecular level, temperature is a measure of the average molecular kinetic energy of a substance. Kinetic energy is the energy of an object in motion, so temperature is related to molecular motion. Because they can flow, liquids along with gases are classified as fluids. Many fluids in process systems are in a liquid state, so a good understanding of the properties of liquids will help you understand how many systems operate. One of the basic characteristics of liquids is their tendency to seek their own level. In other words, liquids try to rise or fall to the same height at all points. We can demonstrate this with a carpenter's level. It consists of two cylinders connected by a hose. There's an equal amount of water in each cylinder. If we add more water to one cylinder, the level rises in the other cylinder to maintain an equal level. Now, if we pour out some water in one of the cylinders, the level drops in the other cylinder to maintain an equal level. Another important property of liquids is their ability to flow, but some liquids flow more easily than others. The ability of a liquid to flow is related to a property called viscosity. Viscosity is a liquid's resistance to flow. A liquid with a low viscosity is less resistant to flow, so it flows more easily than a liquid with a high viscosity. That's why a thinner, low viscosity oil flows more easily than a thicker, high viscosity oil. The viscosity of a liquid can change with changes in temperature. For this reason, heat is often applied to fuel oil pipes in cold weather. Heat may be applied using electrical conductors under the insulation or small tubes that carry steam. Applying heat to piping this way is called heat tracing. Heating the fuel oil decreases its viscosity and allows it to flow more easily. On the other hand, lubricating oils are often cooled in lube oil coolers to maintain their viscosity and lubricating ability. If lube oil is overheated, its viscosity and lubricating ability are decreased. As a result, it may not adequately lubricate bearings or other components. Another property of liquids is wetting. When you pour liquid out of a container, some of the liquid clings to the walls, so the inside of the container remains wet. Surface wetting is a result of the adhesive forces between the liquid molecules and the molecules of the container. Adhesive forces are molecular forces between dissimilar molecules. When a chemical drum is emptied, there is often some surface wetting inside the drum. Sometimes chemical drums are reused to hold different substances. To keep different chemicals from mixing, the drums are often rinsed after they're emptied. Then they're allowed to dry completely before they're refilled. The next characteristic of liquids we're going to look at is called capillary action. If we place a tube into a container of liquid, the liquid tends to rise in the tube. The liquid level in the tube is higher than the liquid level in the container. This is the result of capillary action. As with wetting, capillary action is explained by the adhesive forces between the liquid and the tube. These adhesive forces actually pull the liquid molecules up into the tube. Capillary action stops when the weight of the liquid in the tube is equal to the adhesive forces pulling the liquid into the tube. Everybody knows that some things float in liquids and some things don't. The property that causes things to float is buoyancy, or buoyant force. An object placed in a liquid always displaces some of the liquid. The weight of the liquid displaced is equal to the amount of buoyant force pushing up on the object. A floating object displaces an amount of liquid whose weight is exactly equal to the object's weight. A sinking object displaces an amount of liquid whose weight is less than the object's weight. With liquids, two other properties you need to be familiar with are specific gravity and density. The two are closely related, so we'll consider them together. Liquids don't have definite shapes, but they do have definite volumes. Knowing the volume of a liquid can help you to figure out its density. Specifically, the density of a liquid is its mass divided by its volume. Mass is normally expressed in terms of weight. For example, a cubic foot of water weighs about 62.4 pounds, so the density of water is 62.4 pounds per cubic foot. You can also calculate the density of a liquid if you know its specific gravity. Specific gravity is commonly used to measure the concentrations of solutions, such as acids. This measurement can be made with a hydrometer. You've probably seen one that checks the battery acid in your car. The specific gravity of a liquid is the weight of a volume of the liquid divided by the weight of the same volume of water. Water is used as a standard because it's the most common liquid. It's given a specific gravity of 1. To take an example, the specific gravity of sulfuric acid is about 1.8. So sulfuric acid weighs about 1.8 times as much as water. If the specific gravity of sulfuric acid is 1.8, then sulfuric acid weighs 1.8 times as much as water. This also means that sulfuric acid is 1.8 times as dense as water. Therefore, you can calculate the density of sulfuric acid by multiplying 1.8 times the density of water, which is 62.4 pounds per cubic foot. Sulfuric acid has a density of about 112.3 pounds per cubic foot. Many fluids and process systems are in a liquid state. The temperatures and pressures at which systems operate can have important effects on liquids. In liquids, there are cohesive forces between the molecules, but these forces are fairly weak. As a result, the molecules can move around freely. Temperature changes affect this molecular motion. When a liquid is heated, the molecular motion increases. At a high enough temperature, the forces holding the molecules together are overcome. Then some of the molecules separate from the liquid and are released as a gas. In the case of water, this is the point at which the water boils into steam. When the temperature of a liquid is decreased, the molecular motion slows down. At the freezing point, the molecules form a solid crystal structure, such as ice. So one of the most important effects of temperature on liquids is the possible change in the state or phase of matter. If the temperature is increased, a liquid can be changed into a gas. If the temperature is decreased, a liquid can be changed into a solid. Let's turn now from temperature to pressure. By definition, pressure is force applied over an area. In an open container, pressure is affected primarily by the weight of the liquid applied over a given area. These circles represent liquid molecules. If we focus on the bottom of the container, the pressure exerted there is the total weight of the liquid divided by the area of the container's bottom. The pressure exerted on the side of the container is a result of the force of the liquid pushing outward. The force pushing outward is a result of the weight of the molecules above. This means that the pressure in a liquid varies with its height or depth. As we move upward, there are fewer molecules of liquid above. As a result, the pressure in a liquid is greater the deeper you go in the liquid. As the level decreases, the pressure at the bottom decreases. As the level increases, the pressure increases. In this topic, we looked at many of the important physical properties associated with liquids. We also saw some of the main effects of temperature and pressure on liquids. Now's a good time to review your understanding of the material by trying a couple of practice questions. Lubricating oils are often cooled in lube oil coolers to maintain their viscosity and lubricating ability. If lube oil is overheated, its viscosity and lubricating ability are decreased. As a result, it may not adequately lubricate bearings or other components. This means that the pressure in a liquid varies with its height or depth. As we move upward, there are fewer molecules of liquid above. As a result, the pressure in a liquid is greater the deeper you go in the liquid. In this topic, we looked at many of the important physical properties associated with liquids. We also saw some of the main effects of temperature and pressure on liquids. Electric motors provide the mechanical energy that's needed to operate a wide variety of equipment in industrial facilities. For example, pumps, agitators, fans, compressors, and motor-operated actuators typically depend on electric motors to function. An electric motor is a device that converts electrical energy into mechanical energy. This mechanical energy is in the form of a turning motion. The turning motion can be used to drive a load that is coupled to the motor. The turning motion is produced by the interaction of magnetic fields that are created in the motor. In fact, the movement of an object, such as the rotating part of a motor, as a result of the interaction between magnetic fields, is called motor action. To understand how electric motors operate, it's helpful to start with a simple example of how a magnetic field can be created. This illustration represents a section of wire with current flowing through it from negative to positive. The flow of current through the wire produces a magnetic field around the wire. The magnetic field consists of a series of lines known as magnetic lines of flux. All motors work because of the interaction of two or more separate magnetic fields. The interaction between the magnetic fields can be used to create rotary motion in a motor. We can use an illustration to see how this is done. In this illustration, a loop of wire is positioned in the magnetic field created by two permanent magnets. The loop is connected to a source of direct current, or DC power, which is not shown. Current flows from the negative side of the DC power source through the loop to the positive side. The current flow produces magnetic lines of flux that are perpendicular to the loop. As a result of the magnetic field around the loop, magnetic poles are created. In this case, the poles are perpendicular to the loop. The North Pole is here, and the South Pole is here. In order to show how the magnetic field around the loop interacts with the magnetic field of the permanent magnets, we'll represent the poles created by the loop with a simple bar magnet. The bar magnet is pivoted so that it is free to rotate. Now we can see that there is a pair of each type of magnetic pole in this situation. There are two north poles, which are next to each other, and two south poles, which are also next to each other. Like poles repel each other, so the interaction of the magnetic fields causes the bar magnet to rotate, and that's an example of motor action. As the bar magnet rotates, the repelling forces decrease because the like poles are getting farther apart. However, unlike poles attract each other. The bar magnet's north pole is attracted to this permanent magnet's south pole, and the bar magnet's south pole is attracted to this permanent magnet's north pole. The attracting forces increase as the unlike poles get closer to each other. So when the unlike magnetic poles are closest to each other, the attracting forces are the greatest. At this point, the bar magnet would stop rotating unless its momentum is great enough to carry it past the poles of the permanent magnet. This example illustrates only part of the rotary motion that's needed for a motor to operate. To keep the bar magnet rotating, the polarity of one of the magnets must be changed. Real motors use magnetic fields that change polarities to produce a continuous rotary motion. The way that this is done depends on the type of motor and whether it operates on alternating current or direct current. However, the basic principles that we've gone over here apply to all motors. A motor works because of the interaction of magnetic fields. In this simplified example, one field is produced by a bar magnet, and a second field is provided by two permanent magnets. The interaction between the two fields produces a turning motion. In other words, they cause the bar magnet to turn. However, the movement of the bar magnet would stop when its south pole is next to this permanent magnet's north pole, and its north pole is next to this permanent magnet's south pole, unless conditions change. One way to continue the bar magnet's rotation is to change the polarity of one set of magnetic poles. In an AC motor, this is accomplished using wires coiled around iron cores to form electromagnets. The electromagnets take the place of the permanent magnets used earlier. To explain how this works, we'll start with a single wire coiled around a single iron core. When current is supplied to the coil, magnetic flux lines are produced. When current flows through a wire that's shaped into a coil, the individual flux lines that are produced join together to create one large magnetic field. The core serves to concentrate this field so that it can have a maximum effect. Current flow through the coil creates a north pole and a south pole. Most AC motors have at least two coils in series. This illustration shows two coils around two iron cores. The two coils are connected in series. Alternating current, or AC, flows through the coils in one direction, and then reverses and flows in the opposite direction. As the direction of current flow alternates, the polarity of the coils changes. The alternating polarity can be used to produce continuous rotary motion in an AC motor. We can see how this works by adding a bar magnet between the two coils in our illustration. The bar magnet is the rotating part of the motor in this example. It's called the rotor. The two coils are the stationary part of the motor, which is known as the stator. Every AC motor, regardless of how it's designed, has a rotor and a stator. The rotor and the stator have magnetic fields that interact to produce continuous rotary motion. The like poles repel each other, so the rotor begins to rotate. The rotor's momentum and the attraction of its poles to the unlike stator poles also contribute to the rotation. As the rotor is turning, the current flow through the coils reverses direction, which causes the poles in the stator to reverse. So once again, the like poles are next to each other. The like poles repel each other, and the rotor continues to turn. As the rotor turns, the current flow reverses direction again, changing the polarities of the stator coils, and the rotor continues to turn. This cycle continually repeats, which results in continuous rotary motion. In this example, the stator has two coils of wire. These coils can also be referred to as poles, since they become north or south poles during normal motor operation. Keep in mind that the example of AC motor operation we've used has been simplified to help make things clear. For example, a motor with multiple poles works in much the same way as a motor with only two poles. Also, the rotor in an AC motor is some form of electromagnet rather than the bar magnet we used in our example. Although AC motors are the most common type of motor used in industry, direct current or DC motors are also used. One common use for a DC motor is as a backup motor for a critical process. DC motors can run on the direct current supplied by a battery when there is a failure in the alternating current supplied to an AC motor. For example, this DC motor is used with a backup pump that supplies oil to the bearings in a large piece of equipment. Normally, an AC motor drives a separate pump that supplies oil to the bearings. But if that motor fails, the DC motor-driven pump can be used to provide the oil. This is an illustration of a DC motor. In this simplified example, the stator consists of two permanent magnets. The rotating part, which is shown as a loop of wire, is called the armature. The armature is connected to a source of DC power. These two components are called brushes. The brushes are connected to a DC power source. A conducting ring, known as a commutator, is mounted on the end of the armature. The commutator is not a solid ring. It consists of conducting segments that are separated from each other. During operation, the commutator makes sliding contact with the brushes. Current flows from the negative side of the DC power source through one brush to a commutator segment. The current then flows through the armature in this direction, back through the other commutator segment to the other brush, and to the positive side of the power source. The poles are perpendicular to the armature. So when current is supplied to the armature, motor action is produced. The interaction between the stator's magnetic field and the armature's magnetic field causes the armature to rotate. Even though the armature has turned, the current still flows from the negative side of the power source through the armature to the positive side of the power source. However, the commutator has physically changed the direction in which the current flows through the armature. This change in direction changes the polarity of the magnetic field created by the armature. So the brushes and the commutator in a DC motor enable the armature to change its magnetic field, and as a result, the armature turns continuously. The example we used to explain the operation of a DC motor was simplified to help make things clear. Both the construction and operation of actual DC motors are more complex. For example, the stator in a DC motor is usually an electromagnet, not a permanent magnet. Well, in this topic, we looked at basic motor theory, and we looked at the fundamentals of both AC motors and DC motors. Now try some practice questions that relate to this material. Now we can see that there is a pair of each type of magnetic pole in this situation. There are two north poles, which are next to each other, and two south poles, which are also next to each other. Like poles repel each other, so the interaction of the magnetic fields causes the bar magnet to rotate, and that's an example of motor action. Alternating current, or AC, flows through the coils in one direction, and then reverses and flows in the opposite direction. So when current is supplied to the armature, motor action is produced. The interaction between the stator's magnetic field and the armature's magnetic field causes the armature to rotate. This is a typical AC motor. Its external parts include a frame, a shroud, and an end bell. The frame houses the stator and the rotor, and it also provides a means to mount the motor to a foundation. This motor is designed to be mounted horizontally. But not all motors are mounted horizontally. In some situations, motors are mounted vertically to drive vertically mounted shafts. For example, these vertically mounted motors drive sump pumps. Motors can also have a variety of frame designs. Open frame motors are commonly used in non-hazardous areas. But some process applications require motors to be completely enclosed. Electrical equipment can cause explosions in areas where there are flammable liquids, gases, or dust. In these areas, totally enclosed, explosion-proof motors are generally used. During normal operation, an AC motor produces heat as a result of current flowing through it. Many motors use fans and ventilation openings to get rid of heat. On this particular motor, the shroud has openings to admit air into the motor to cool it. A fan cools the motor by pulling in air through ventilation openings in the shroud. As air is blown across the motor frame, the air carries away heat produced by the motor. Smaller motors may be cooled by simply letting heat escape from the motor frame. Other designs are also used to remove heat. For example, this motor has a set of fins. The current rating is the amount of current the motor can draw during normal operation without being damaged. The amount of current a motor actually draws usually varies over a range. The amount of current drawn at any one time depends on the load on the motor. In other words, how hard the motor is working. Horsepower is a rating of how much mechanical power the motor can be expected to produce. The operating speed rating refers to how fast the rotor is designed to rotate during normal operation. Most of the information on a motor's nameplate can be used to determine what a motor's normal operating conditions are. This information is important when a motor is selected for a given application, and it may also be important to maintenance personnel. Let's continue now by looking at some of the internal parts of a typical AC motor. This is a stator from an AC motor. The end bells in the rotor have been removed to see the stator better. The stator contains several coils of wire called stator windings that surround the rotor. Current flow through the stator windings produces magnetic fields. The windings have been dipped in an insulating varnish and then baked. The fins provide additional surface area to dissipate heat into the surrounding air. Another important part of a typical AC motor are the end bells. The end bells house the bearings that support the motor's shaft. Bearings provide support for the rotor shaft and allow the rotor to turn. For proper operation, bearings must be kept lubricated. Lubrication reduces friction between the bearings parts. There are some motors that use sealed bearings that do not have to be relubricated for the life of the motor. The bearings of some other motors are greased through grease fittings as part of a regular maintenance schedule. Other motors use a constant level oiler. A constant level oiler holds a small supply of oil that drains by gravity into the bearing. The design of the constant level oiler allows the operator to look at the level in the reservoir and add more oil when necessary. A connection box on this motor protects the motor's wires or leads from damage. These wires electrically connect the motor to a source of AC power. All motors are designed to operate according to certain specifications. Many of these specifications are listed on the motor's nameplate. For example, this nameplate includes information about voltage in volts, current in full load amps or FLA, horsepower designated as HP, and operating speed in revolutions per minute or RPM. The voltage rating that's shown is the motor's normal operating voltage. A motor can be damaged if it is operated for extended periods of time at a voltage other than its rated voltage. The varnish insulates the windings from each other and prevents short circuits or grounds that could damage the windings. The rotor is mounted on a shaft. This rotor is made of conducting bars that are shorted together by end rings. The rotor bars with their end rings are attached to a shaft so that the whole assembly can turn together. As the magnetic fields generated by the stator windings pass through the rotor, a voltage is induced in the rotor. The voltage creates current flow through the rotor, which creates another magnetic field. The interaction of the magnetic fields generated by the rotor and the stator windings produces motor action, which causes the rotor to turn. In this part of the program, we'll look at a disassembled DC motor to identify and discuss its parts. The major parts of this DC motor include the frame used to house the stator and armature, the stator, which you may also hear referred to as the field, the armature, and end bells. The stator is made of coils of wire that are wrapped around iron cores. The coils are electrically connected to a DC power source. The armature contains several loops of wire that are wound back and forth. All of the loops make an electrical connection to the motor's commutator segments. The electrical connections to the commutator segments are protected and held in place under a wrapping of varnish-coated fibers. Current flows from one commutator segment through the armature and back through another commutator segment. The commutator makes sliding contact with a set of brushes. The brushes, which fit in holders, are held against the commutator by springs to maintain contact and to provide a path for current flow from the power source to the commutator. Brushes are a frequent maintenance item for DC motors. Because they rub against the commutator, they wear down, so they must be replaced periodically. Sparking or arcing near the brushes or on the commutator can mean that the brushes need to be replaced, or that they're not making good contact with the commutator. In addition, brushes can chip, which impairs their effectiveness. The commutator should also be checked periodically. Any scoring or grooving on the face of the commutator may indicate a problem. In this topic, we looked at the parts of both AC motors and DC motors, and we discussed their functions. Now try some practice questions that relate to this material. Bearings provide support for the rotor shaft and allow the rotor to turn. The commutator makes sliding contact with a set of brushes. The brushes, which fit in holders, are held against the commutator by springs to maintain contact and to provide a path for current flow from the power source to the commutator. Many of the processes in a plant depend on electrical equipment. In order for this equipment to function properly, it must have a continuous, reliable source of electricity to power it. An electrical distribution system supplies power to meet the needs of process equipment. The distribution system consists of equipment that brings electric power into the plant, converts that power to usable voltages for process equipment, distributes the power throughout the plant, and protects components in the system from damage. As an operator, you're likely to work with electrical equipment on a regular basis, so you need to have a basic understanding of your plant's electrical distribution system. Many plants receive all of their electric power from an off-site source, such as an electric power company. The power that's supplied to a plant can be generated in a number of different ways. One common source of electricity is power plants that convert the energy in fossil fuels, such as coal, oil, or natural gas, into electrical energy. Off-site electricity may also come from nuclear plants, which harness the atomic energy produced by the splitting of an atom's nucleus. Another possible source of electricity is hydroelectric plants, which use the energy of falling water to generate electricity. In any case, once electricity is generated at power plants, it must be transmitted, sometimes over long distances, to the facility. Power transmission lines bring electric power into a facility. In this case, the voltage coming into the facility is 69,000 volts. Other voltages are also commonly used, depending on the power supply system and the requirements of the facility. Here, the incoming voltage is 34,500 volts. For most industrial customers, electric power comes into the plant at what is known as the main substation. Voltage can be changed from one value to another using a device called a transformer. A transformer increases or decreases voltage for various uses. At this plant, the main substation transformer takes the incoming voltage, 69,000 volts, and reduces it to a level the plant can use, which in this case is 13,200 volts. Overhead cables take the 13,200 volts of power from the main substation and distribute the power throughout the plant. The voltage leaving the main substation is often referred to as the distribution voltage. Plants can use different distribution voltages. Some other common voltages are 13,800 volts and 2,300 volts. However, since specific plant equipment may require lower voltages, the distribution voltage may need to be reduced further by transformers. Not all plants receive electric power from an off-site source. Some plants combine power from an off-site source with power they produce themselves on-site, or they produce all of their own power on-site. Some on-site power generating facilities are part of a cogeneration process, which provides the plant with electric power as well as process steam. Let's look at some of the ways that industrial facilities can generate electricity on-site. One way to generate electricity is by using steam that's produced in a boiler. With this method, fuel is ignited and burned in the boiler. Many boilers burn fossil fuels, but others burn fuels like wood chips or other combustible materials. In any case, the burning fuel releases heat or thermal energy, which is absorbed by water flowing through tubes in the boiler. When the water gets hot enough, it boils, producing steam. Steam from the boiler is supplied to a turbine generator set, which converts the thermal energy in the steam to electrical energy in 2 steps. In the first step, the steam is forced through a series of turbine blades. Some of the blades are fixed and direct the steam through the turbine. Other blades are mounted on a shaft inside the turbine. As the steam passes between the blades, an energy conversion occurs which causes the turbine shaft to rotate. In the turbine, the thermal energy is converted to mechanical energy. The turbine shaft is connected to the generator shaft. As the turbine drives the generator, the mechanical energy is converted to electrical energy. The output from the generator is electricity that can then be supplied to the plant's electrical distribution system. This particular generator produces 13,200 volts, but other generators can produce different voltages. Steam turbines aren't the only devices used to drive generators. For example, some generators are driven by gas turbines. Like steam turbines, gas turbines take energy from a fluid moving through blades. Gas turbines use hot combustion gas that's produced by burning a mixture of fuel and air. In fact, gas turbines are sometimes called combustion turbines. As the fuel and air mixture is ignited and burned, the hot gas expands and flows rapidly through the turbine blades. The thermal energy in the hot gas is converted to mechanical energy, which causes the turbine shaft to rotate. This, in turn, drives the generator and produces electric power. Gas turbines are often used for emergency purposes as a source of backup power. They provide enough power to keep essential equipment and services going until repairs can be made to the main power generation system. Gas turbines can also be used in combined cycle arrangements. In a combined cycle system, exhaust heat from a gas turbine is used to boil water and make steam for a steam turbine. Using an exhaust product from one turbine to provide heat for another turbine increases power generation efficiency. Diesel engines are also frequently used to drive generators. Basically, a diesel engine is an internal combustion engine that burns diesel fuel instead of gasoline. In a diesel engine, a fuel and air mixture is compressed and burned, much as it is in a car engine. This internal combustion turns a crankshaft, which provides a mechanical motion for a generator to produce electricity. Some plants use diesels as emergency power generators. Diesels can be set up to start automatically when the main power source is lost. In addition, some diesels are portable and can be used to generate power when other power sources are unavailable. In this topic, we saw how electric power comes into a plant from an off-site source, and we looked at ways in which power can be generated on-site. Now take a moment to try some practice questions on this material. For most industrial customers, electric power comes into the plant at what is known as the main substation. A substation is an area in which voltage is changed from one value to another. When steam from a boiler passes through a turbine, thermal energy in the steam is converted to mechanical energy. This causes the turbine shaft to rotate and drive a generator to produce electricity. In order for the electric power that's supplied to a plant to be utilized, it has to be distributed at the proper voltage to the equipment that uses it, wherever that equipment's located. That's where an electrical distribution system comes into play. The purpose of an electrical distribution system is to supply power to electrical equipment at its specified or rated voltage. The system has to meet the needs of a wide range of equipment, from large motors that operate at several hundred volts to standard electrical outlets that require much less voltage. Distribution systems also contain equipment that has a protective function. Protective equipment helps minimize damage to the system during abnormal conditions, such as short circuits, overloads, and voltage surges caused by lightning. Distribution systems vary widely, depending on a plant's power requirements and its processes. We'll look at one example, but your plant's system and the equipment in it may be different. Despite the differences, you should still be able to apply what you learn here to just about any system. We'll use this simple block diagram as a starting point for our explanation of a distribution system. The system represented here has a main substation, which takes incoming power and reduces its voltage, as well as two smaller substations called unit substations. The unit substations reduce the voltage from the main substation to levels that parts of the plant can use. The distribution system also has various loads. Load refers to a circuit or piece of equipment that uses the electric power. The electric power flows through the system along different paths or circuits. In this system, the distribution voltage leaving the main substation is 13,200 volts, or 13.2 kV. kV stands for kilovolts, or thousands of volts. The part of the system that carries the 13.2 kV is called a bus. A bus distributes power in an electrical distribution system, and it operates at a specific voltage. The 13.2 kV bus feeds the two unit substations, which reduce the voltage to a level that's usable by the equipment being supplied. This unit substation reduces the 13.2 kV to 2.3 kV. This part of the circuit is a 2.3 kV bus, since it supplies 2,300 volts to these loads. Now, this unit substation reduces the voltage from 13.2 kV to 480 volts. This part of the circuit is a 480 volt bus, since it supplies 480 volts to these loads. Most electrical distribution systems have several buses at different voltages. They may also have more than one bus at a given voltage. For example, several 480 volt buses may be needed if the plant has a lot of 480 volt loads. A plant's electrical distribution system is often represented on electrical diagrams. These diagrams typically include information about bus voltages and system components, which can help operators pinpoint the source of a problem. This diagram represents the system we saw earlier. Voltage comes into the main substation at 69 kV and is reduced to 13.2 kV. The voltage is reduced by the main transformer, and this is the electrical symbol for a transformer. Now, this symbol represents a circuit breaker. Circuit breakers have two basic functions. First, they protect loads from potentially damaging conditions by automatically tripping, that is, by interrupting current flow. After the abnormal conditions have been corrected, circuit breakers can be reset to restore a path for current flow to equipment that needs it. Circuit breakers also provide a means of manually isolating loads from their source of power. This helps to protect personnel when maintenance is needed. The electrical diagram for this system also shows the buses that we mentioned earlier, including the 13.2 kV bus, the 2.3 kV bus, and the 480 volt bus. Let's take a closer look at the 2.3 kV bus. This transformer converts the distribution voltage, 13.2 kV, to 2.3 kV. There are circuit breakers on each side of the transformer. The 2.3 kV bus supplies power to 3 different loads. 2 of the loads are motors that are fed directly from the 2.3 kV bus. Each of the motors is protected by a circuit breaker. The other load is a separate bus, in this case a 480 volt bus. A transformer reduces the voltage from the 2.3 kV bus to 480 volts. The transformer also has circuit breakers on each side. 2 motors serve as loads off the 480 volt bus, and each motor is protected by a circuit breaker. Now that we've looked at the 2.3 kV bus, let's do the same for this 480 volt bus. As you can see, a transformer reduces the distribution voltage, 13.2 kV, to 480 volts. The 480 volt bus provides electric power to 2 transformers. One of the transformers reduces the voltage from 480 volts to 240 volts for a lighting circuit, which powers the lights in the area. The other transformer reduces the voltage from 480 volts to 110 volts for a circuit that supplies several 110 volt loads in the area. One load is a motor. The device that protects the motor is a fuse. A fuse works much like a circuit breaker. That is, it interrupts current flow if the current flow exceeds a certain value. But unlike a circuit breaker, a fuse can't be reset. When a fuse operates, it burns open and has to be replaced. Electrical diagrams can be extremely helpful when you're trying to isolate problems with equipment. For example, suppose this 110 volt motor stops working. After ruling out any mechanical or electrical causes at the motor, you can use the diagram to investigate possible causes in the system. Now, there are different ways to troubleshoot a problem. One way is to check the fuses and circuit breakers to see if a fuse blew or if a circuit breaker tripped. The diagram helps the operator determine where the fuses and circuit breakers are for a particular system. By working backwards from the motor, it's possible to figure out where the power is being interrupted. As an operator, you hear a lot of talk about safety, and you're likely to see warning signs around the plant. One thing you should never do is take safety for granted. Many people think that accidents can never happen to them, that safety's for other people. But carelessness and improper shortcuts are 2 big causes of industrial accidents and injuries. Safety is especially important when you're working around electricity. You can't see electricity, but if you don't take precautions, it can be deadly. Your plant probably has rules and guidelines to help people do their jobs safely. Follow these rules to the letter when you work around electrical equipment. A knowledge of basic electrical safety rules, combined with a good understanding of your company's policies, can reduce the hazards related to electrical equipment. Your plant probably uses a series of overhead lines to carry electric power. At some point, you may come across a downed power line. You should always assume that downed power lines are live, and a live line can electrocute you or cause a fire. If you see a downed line, report it immediately. Cables that carry electric power at a plant may be installed in a protective pipe or tubing called conduit, and most cables and wires are insulated. However, cuts or breaks can decrease the effectiveness of the insulation. This could result in a fire, an electrical shock, or arcing. Arcing is the discharge of electricity across a gap in a circuit. Another potential hazard is a leak in a pipe. Leaks in pipes can result in liquid coming into contact with electrical equipment. You can get shocked, for example, if you're trying to identify the source of a leak and you accidentally touch energized equipment. In addition, some liquids can start a fire when they get on energized equipment. Be careful anytime you have to check electrical equipment closely. In some cases, you may smell insulation burning or see arcing, which tells you that current is going where it's not supposed to. If you work around electrical equipment, it's possible you may be faced with emergency situations, such as treating a victim of electrical shock. Your company may have its own specific procedures for emergencies, but here are a few general guidelines to follow if you're trying to help an electrical shock victim and the victim is touching a power source. First, try to cut off the power supply if possible. If you can't do that, try using a non-conducting pole or rope to separate the victim from the electrical source. In some cases, you can even use your belt. But what you should not do is touch the victim with any part of your body. If you touch the victim with any part of your body, you may get an electrical shock too. We've just seen some basic guidelines for dealing with an electrical shock victim. In general, the goal is to isolate the victim from the source of electricity without creating a path for current flow through yourself or others. Learn your company's procedures and follow them to the letter if you're ever faced with this situation. Another hazard that you may have to deal with is an electrical fire. Electrical fires can happen for many reasons, and it may be part of your job to respond to them. Generally, the first thing to do is report the fire. Reporting the fire will set in motion other emergency actions, such as isolating circuits to prevent injury and equipment damage. Then try to cut off power if possible. This takes away the source of ignition. If you're going to put the fire out, be sure to use the right type of fire extinguisher. Fire extinguishers are classified by the type of fire they're designed to extinguish. A Class C fire extinguisher is used for electrical fires. Class C extinguishers often contain carbon dioxide, CO2, which is ideal for electrical fires because CO2 puts out the fire without conducting electricity. You should never use water to put out an electrical fire. Water conducts electricity, and it can cause an explosion or create hazardous paths for current flow. By now, you should be aware of the main concerns related to electrical fires. However, you should still learn the procedures and safety measures that apply to the equipment and hazards in your plant. Our focus in this topic was on power distribution. We looked at the main components in a typical electrical distribution system, and we explored some key safety issues associated with electrical equipment. Take some time now to try a couple of practice questions on this material. Now, this symbol represents a circuit breaker. Circuit breakers have two basic functions. First, they protect loads from potentially damaging conditions by automatically tripping, that is, by interrupting current flow. After the abnormal conditions have been corrected, circuit breakers can be reset to restore a path for current flow to equipment that needs it. Circuit breakers also provide a means of manually isolating loads from their source of power. This helps to protect personnel when maintenance is needed. Another hazard that you may have to deal with is an electrical fire. Electrical fires can happen for many reasons, and it may be part of your job to respond to them. Generally, the first thing to do is report the fire. Reporting the fire will set in motion other emergency actions, such as isolating circuits to prevent injury and equipment damage. Then try to cut off power if possible. This takes away the source of ignition. If you're going to put the fire out, be sure to use the right type of fire extinguisher. Fire extinguishers are classified by the type of fire they're designed to extinguish. An integral component of a typical motor control system is a motor controller. A motor controller is a device or a group of devices whose purpose is to control and protect a motor. Physically, a motor controller may be located quite a distance away from the motor that it controls. Electrically, the motor controller is located between the facility's power supply and the motor. Motor controllers for the motors in an area of a facility are often grouped together inside a common housing called a motor control center, or MCC for short. In many cases, an MCC houses the controllers for the motors in a particular process. An MCC may also contain other electrical devices, such as circuit breakers and switches. One device that is often part of a motor controller is an electromagnetic switch known as a contactor or motor starter. When the contactor is operated, it allows current to pass through the controller to the motor. This is a simplified illustration of one type of contactor. During operation, current is supplied to a coil inside the contactor. This coil is known as the operating coil or the M coil. An iron core inside the M coil concentrates the magnetic field. When the M coil is energized, it becomes an electromagnet and attracts an armature. This moves a set of movable contacts against a set of stationary contacts. The armature is connected to a pair of springs, which are compressed as the armature is pulled down. When the contacts close, a complete path for current flow is established through the controller to the motor. When the M coil is de-energized, the electromagnetic field is removed, and the springs push the armature back to its original position, separating the two contacts. One advantage of using a contactor in an AC motor controller is that it can be energized from a remote location using a voltage that is lower than the motor's operating voltage. The power circuit is energized or de-energized by devices operated by the lower voltage control circuit. This protects personnel from high voltage hazards when they start and stop high voltage motors. An AC motor controller typically has 3 sets of contacts, one set for each of the 3 phases of power in the AC power circuit. A motor controller may also have additional sets of contacts called auxiliary contacts. Auxiliary contacts are usually attached to the armature and operated by it. These contacts are used to perform auxiliary control functions, such as providing current for indicating lights, like the ones used to indicate whether a motor is on or off. Now, in addition to controlling the operation of a motor, motor controllers usually protect the motor as well. For example, motors are rated to deliver a certain amount of power. If demand on the motor increases, current flow through the motor increases. If the current is allowed to exceed the rated capacity of the motor's stator windings could be damaged. In addition, the rotor and possibly other parts could be damaged by excessive current. Motor controllers typically contain overload devices. When these devices detect excessive levels of current that are associated with overload conditions, they shut down the motor before damage occurs. When an overload causes a motor to shut down, the cause of the overload must be determined. After the problem is corrected, the motor can be restarted. Many motor controllers have a reset button that must be operated to reset the controller after an overload. As a general rule, a motor controller should be reset only once after an overload. If it's reset more than once and the motor is started over and over, the motor's windings could be damaged. This is a simplified electrical diagram of an AC motor controller. Electrical diagrams use letters, numbers, symbols, and lines to identify components and show how they're connected electrically. The controller has a motor circuit or power circuit that provides power to the motor, and a control circuit that can open or close the power circuit. A power source, which is not shown on the diagram, is connected to the power circuit through the line leads labeled L1, L2, and L3. The line leads are connected to 3 main contacts, which are labeled with the letter M. The main contacts are normally open, which means that they're open when they're in the relaxed or de-energized state. The main contacts are connected to 3 overload devices, which are connected to 3 motor leads labeled T1, T2, and T3. The motor leads are connected to the motor. A step-down transformer is also connected to the power circuit. The transformer lowers or steps down the voltage used in the power circuit to a lower value that is used to operate the control circuit. The transformer is connected to a fuse. The fuse protects the motor controller from short circuits. If a short occurs in the control circuit, the fuse will blow, causing an open in the control circuit. The fuse is connected to stop and start buttons. The control circuit also has an operating or M coil and 3 overload contacts. The overload contacts, which are labeled OL, are normally closed. Pushing the start button energizes the control circuit, including the M coil. All of the contacts labeled M are operated by the M coil. When the M coil is energized, it closes the M contacts, and power can be provided to the motor. In this example, the start button is designed to be pushed in and released. After the start button has been released, maintaining contacts, labeled capital M, small a, remain closed to maintain current flow to the M coil. The maintaining contacts are auxiliary contacts operated by the M coil. If an overload occurs, the overload devices open the overload contacts. Opening the overload contacts opens the control circuit, which stops current flow to the M coil. When the M coil is de-energized, the M contacts open. As a result, the path for current to flow to the motor is interrupted and the motor stops. In order to stop the motor during normal operation, the stop button is pushed. Pushing the stop button opens the control circuit, which stops current flow to the M coil. Now, DC motor controllers are very similar to AC motor controllers. We can use a simplified diagram to see what we mean. Generally speaking, DC motor controllers differ from AC motor controllers in that DC motor controllers use direct current instead of three-phase alternating current. There are only 2 lines in the power circuit of a DC motor controller instead of the 3 lines in an AC motor controller. And DC motor controllers do not use a step-down transformer. The control circuit of a DC motor controller operates using the same level of voltage that powers the motor. Motors are rated to deliver a certain amount of power. If demand on the motor increases, current flow through the motor increases. If the current is allowed to exceed the rated capacity of the motor, it can cause serious damage to the motor's windings. To prevent such damage from occurring, overload devices are installed in most motor controllers. Overload devices protect motors from excessive current. Whenever an excessive current condition occurs, an overload device opens the circuit that supplies power to the controller's contactor or M coil. The de-energized contactor then opens the contacts in the motor controller, interrupting the current flow to the motor, and the motor stops. Overload devices can basically be divided into 2 types: thermal overload devices and magnetic overload devices. Both types of overload devices operate on current. Thermal overload devices operate on the heat generated from current, while magnetic devices operate on the magnetic field generated by current. Thermal overload devices use a heating element, often referred to as a heater. Current flowing to the motor first flows through a heater where it generates heat. The greater the current flow, the more heat is produced. When the level of current flow causes enough heat to be produced, the overload device is activated. We'll look at 2 common thermal overload devices: alloy thermal overload devices, which are commonly called solder pots, and bimetallic overload devices. This is a simplified illustration of part of a solder pot. We can see it has a heater, a ratchet wheel, a rod, and solder, which is an alloy that surrounds the rod. Current in the motor controller's power circuit going to the motor flows through the heater. When current flows through the heater, it generates heat. If the current exceeds the rated value of the overload device, enough heat is generated to melt the solder. Now let's look at the entire solder pot. From this angle, we can see the top of the ratchet wheel here. We can also see that the solder pot has a mechanical linkage, movable contacts, which are in the motor controller's control circuit, and 2 springs. The ratchet wheel, which is set on the rod, holds the mechanical linkage in place. The movable contacts are attached to the mechanical linkage, and the stationary contacts are positioned in the casing of the overload device. The linkage spring holds the mechanical linkage against the ratchet wheel, and the contact spring pushes against the movable contacts. While the solder is solid, it prevents the ratchet wheel and the rod from turning. As long as the ratchet wheel and the rod do not turn, the contacts remain closed, and a complete circuit to the motor controller's main contactor, or M coil, is maintained. The contact spring is positioned so that its force works on the mechanical linkage to attempt to turn the ratchet wheel. When the current level causes the heater to generate enough heat to melt the solder, the liquid solder cannot hold the rod, so the force of the contact spring causes the ratchet wheel to rotate. As the wheel turns, the linkage moves, opening the contacts of the overload device and interrupting the current flow in the control circuit to the M coil. As a result, contacts in the motor controller are opened, which interrupts the current flow in the power circuit to the motor, and the motor stops. When the current in the power circuit stops flowing through the heater stops generating heat. When the heater stops generating heat, the solder then cools and becomes solid again. When a reset button is pushed, The contacts of the overload device close, which makes it possible to restart the motor by supplying current to the M-coil. Another typical thermal overload device is a bimetallic device, like the one illustrated here. This device consists of a heater, which is in the motor controller's power circuit, a bimetallic strip, which is a strip made up of two different metals that are bonded together, a spring-loaded mechanical linkage, a set of contacts, which is in the motor controller's control circuit, and a reset button. The two metals in the bimetallic strip expand at different rates when the strip is heated by the heater. Under normal circumstances, the bimetallic strip holds the mechanical linkage in place, keeping a set of contacts closed so that there is a complete path for current to flow to the motor controller's M-coil. When the current level in the power circuit exceeds the rated value of the overload device, enough heat is generated by the current flow through the heater to cause the bimetallic strip to bend so that it releases the mechanical linkage. The strip bends because the two metals in the strip expand at different rates. When the mechanical linkage is released, the force of the springs pulls the contacts open, which interrupts the current flow in the control circuit to the controller's M-coil. As a result, contacts in the motor controller open, which interrupts current flow in the power circuit to the motor, and the motor stops. When the current flow in the power circuit is interrupted, current does not flow through the heater, which stops producing heat, and the bimetallic strip cools. As the strip cools, it contracts and straightens. When the reset button is pushed, the mechanical linkage is moved against the force of the spring so that the linkage is snapped back into its original position. The bimetallic strip once again holds the linkage in place. The linkage holds the overload device's contacts in place, which makes it possible to restart the motor by supplying current to the M-coil. Now that we've looked at thermal overload devices, let's look at a typical magnetic overload device. You may also hear magnetic overload devices called magnetic overload relays. This simplified illustration of a magnetic overload device shows a coil around a metal core and a set of contacts. The contacts are held together by a spring. The overload device's coil is in the motor controller's power circuit, and the contacts are in the control circuit. When the power circuit is energized, current flows through the coil, creating an electromagnetic field. The strength of the electromagnetic field increases as the current level flowing through the coil increases. When the current level gets too high, the strength of the electromagnetic field increases enough to overcome the force of the spring and pulls the contacts apart, which interrupts current flow through the control circuit. As a result, contacts in the motor controller open, current flow to the motor through the power circuit is interrupted, and the motor stops. When the current flow through the power circuit and the coil stops, the electromagnetic field is also interrupted, and the force of the spring pulls the contact back to its original position. In this topic, we looked at the parts and functions of motor controllers and at typical overload devices used to protect motor controllers from overload conditions. Take some time now to try some practice questions that relate to this material. The steps we'll look at for a motor startup are intended as general guidelines that can be applied to starting most AC or DC motors. Keep in mind, though, that they're not intended as a substitute for your facility's procedures. And always keep safety in mind. Motors can pose a number of safety hazards. Loose clothing, for example, can get caught in rotating equipment. During pre-startup checks, the motor, the equipment that the motor is driving, and the rest of the system should be checked. We'll focus, though, on the steps that are concerned with the motor. One important pre-startup check is to check the motor's lubrication system. For proper operation, bearings must be kept lubricated. Lubrication reduces friction between the bearings' parts. Some motors use sealed bearings that do not have to be relubricated for the life of the motor. The bearings of some other motors are greased through grease fittings as part of a regular maintenance schedule. Some motors use constant level oilers, also known as bottle oilers, to lubricate their bearings. The design of the constant level oiler allows the operator to look at the level in the reservoir and add more oil when necessary. When a constant level oiler is used, oil flows into the bearings by gravity. Another important pre-startup check is checking the motor's cooling system. For example, this motor is cooled by a fan mounted on its shaft. The motor's ventilation openings are checked to make sure that they're clear of obstructions that could restrict cooling airflow. It's also a good idea to check the wires and conduit associated with the motor for signs of damage. Damaged conduit or loose or frayed wires may result in electrical problems. Some motors may have a grounding strap or ground wire that helps prevent electric shock hazards. It should be checked to make sure that there is a secure connection between the motor and ground. In addition, the motor should be inspected carefully for anything out of the ordinary, such as loose or missing components. The motor controller should be checked to make sure that it's energized and ready for the motor to be started. Depending on your facility's procedures, you may need to notify the control room operator before the motor is started. When all checks are complete, the motor can be started by pressing its start button. Once a motor has been started, it's important to make some operating checks to ensure that the motor operates properly. Operating checks are a vital part of keeping process operations running smoothly. By making these types of checks periodically, an operator may spot potential problems before they become serious. Typically, operators routinely check for proper lubrication, excessive or unusual noise, and excessive heat or vibration. Proper lubrication is an essential part of good motor operation. There are some motors that use sealed bearings that do not have to be relubricated for the life of the motor. Other motors rely on a lubrication system to supply the bearings with grease or oil. If the motor uses a lubrication system, it's important to know how much oil or grease a motor is using. If the motor seems to be using an excessive amount of lubricant, check for leaks. Motors get hot during operation, and they may overheat for several reasons. For example, an overload may result when an excessive load is placed on the motor. You can carefully feel the motor casing to determine if the motor is too hot. In general, if the casing is significantly hotter than it was during previous checks, there may be a problem. You may also be able to detect excessive vibration, which is another common motor problem, by carefully feeling the motor's casing. You should also look over the motor and the equipment it's driving for anything unusual, such as sparking or arcing, which could indicate a short or an open. In addition, listen for unusual sounds. A properly operating motor should make a smooth, steady sound. Excessive noise, knocking, or popping can be a sign of a problem. In addition to looking and listening for symptoms of motor problems, you can also use your sense of smell. Unusual odors may indicate a problem. For example, overheated insulation has a distinctive scent that can indicate a problem such as an electric short. Now, when you're ready to shut down a motor, you first determine the impact that the shutdown will have on the system. Then prepare the system for the shutdown. For example, valves and switches in the process the motor serves may need to be properly positioned before shutdown. Finally, push the stop button for the motor. In this topic, we looked at typical steps for motor startup, and we looked at operating checks that can be made to ensure the proper operation of a typical motor. We also talked about what's involved in a motor shutdown. Take some time now to answer some practice questions that relate to this material. Physically, a motor controller may be located quite a distance away from the motor that it controls. Electrically, the motor controller is located between the facility's power supply and the motor. Pushing the start button energizes the control circuit, including the M coil. All of the contacts labeled M are operated by the M coil. We'll look at two common thermal overload devices: alloy thermal overload devices, which are commonly called solder pots, and bimetallic overload devices. Typically, operators routinely check for proper lubrication, excessive or unusual noise, and excessive heat or vibration. The electrical equipment in a plant normally receives power from an electrical distribution system. An electrical distribution system consists of components that bring power into the plant, convert the power to usable voltages, distribute the power throughout the plant, and protect equipment from damage. Since you're likely to work with electrical equipment on a regular basis, you need to understand how the components in an electrical distribution system function. Some of the main components in a plant's electrical distribution system are transformers. Transformers increase or decrease voltage from one electrical circuit to another. By doing so, they enable an electrical distribution system to provide different voltages to different types of equipment. All transformers work on the principle of electromagnetic induction. The application of this principle enables power to be transferred from one circuit to another, even though there's no physical connection between the circuits. The transformers used in electrical distribution systems operate on alternating current, or AC. Alternating current gets its name from the fact that it reverses direction periodically. In fact, it reverses many times per second. It's easier to understand this characteristic if we look at this graph, which shows how AC voltage would look plotted over time. As the graph indicates, AC voltage increases in a positive direction until it reaches its maximum positive value. Then it returns to zero. Increases in a negative direction until it reaches its maximum negative value. Then returns to zero again. In fact, this cycle of increasing and decreasing voltage values repeats many times per second. To see how this happens, we'll use this illustration of an AC circuit that contains a transformer. The transformer is represented by these two coils of wire called windings. The circuit can be divided into two halves or sides. This side is the primary side. It consists of components that handle power coming into the transformer. In this circuit, the primary side includes an AC power supply, which is represented by this symbol, a switch, and one of the transformer coils called the primary winding. The other side of the circuit is called the secondary side. The secondary side components handle power leaving the transformer. In this circuit, the secondary side includes the other coil of the transformer, which is called the secondary winding, and a load, which in this case is an ammeter. The ammeter indicates current flow in amps through the secondary side of the circuit. During operation, the switch is closed to energize the primary side of the circuit. This causes current to flow from the AC power supply through the switch and the primary winding of the transformer and back to the power supply. As current flows through the primary winding, a magnetic field develops around the winding. The magnetic field is represented here by a series of lines called lines of magnetic flux. The nature of the alternating current that passes through the primary winding causes the magnetic field to expand and collapse repeatedly. As the magnetic field expands and collapses, the flux lines cut across the secondary winding. This induces a voltage in the secondary winding and causes current to flow through the secondary side of the circuit. The ammeter detects the current flow, and its pointer provides a visual indication. As we've just seen, alternating current creates an expanding and contracting magnetic field which induces voltage and enables a transformer to work. Now, the output voltage from a transformer depends on the ratio of the number of turns of wire in the primary winding to the number of turns of wire in the secondary winding. This turns ratio determines whether the transformer increases or decreases voltage and by how much. For example, if there are more turns of wire in the secondary winding than in the primary winding, the output voltage will be higher than the input voltage. In other words, the transformer will increase or step up the voltage. On the other hand, if there are more turns in the primary winding than in the secondary winding, the output voltage will be lower than the input voltage. In this case, the transformer will decrease or step down the voltage. Different kinds of transformers can be used to increase or decrease voltage from one electrical circuit to another. The components that make up these transformers can vary as well. Let's take a look at some basic transformer components now. We'll start with this typical substation transformer. Electricity enters the top of the transformer through power cables. Bushings are used to insulate the cables from the transformer casing. The casing of the transformer provides a housing for the internal parts. Inside the transformer casing are the windings. The windings are usually mounted on an iron core, which concentrates the magnetic field produced in the windings. Besides insulating the windings, the oil also cools the windings, which can produce a lot of heat during normal operation. Some oil-cooled transformers have radiators to make the cooling process more efficient. In the arrangement illustrated here, there's a natural circulation of oil. As the oil picks up heat from the windings, its density decreases, causing it to rise. The warmer oil enters the top of the radiators, where its heat is transferred through the radiators to the surrounding air. As a result, the oil becomes cooler and more dense. The cooler oil sinks to the bottom of the radiators, then re-enters the transformer, where it can pick up more heat from the windings. Some oil-cooled transformers use mechanical devices to aid in cooling. For example, this transformer has a set of fans that move air through the radiators to help transfer the oil's heat to the surrounding air. Transformers can also have oil pumps. They create a forced circulation of oil through the transformer and its radiators. Now, not all transformers use oil to cool their windings. For example, this transformer is air-cooled. It has a set of fans that blow the air that's heated by the windings out of the transformer casing. Screens at the bottom of the transformer let cool air in to replace the heated air. As an operator, you may be responsible for periodically inspecting the transformers at your plant. Inspecting transformers at regular intervals can help in detecting problems before they become serious. An important part of transformer inspections is knowing and following all applicable safety procedures. Safety is an important consideration whenever electrical equipment is involved. Generally, equipment or connections that can cause an electric shock are located out of reach. Equipment or connections that can be reached are often protected by shields or cages. These devices help prevent personnel from coming into contact with energized equipment. Fences are sometimes installed around equipment such as transformers to prevent unauthorized entry. But keep in mind that with or without protective devices, contact with electrical equipment may not be safe. Even low-voltage equipment can cause injuries. And energized transformers often use high enough voltages to cause death if the proper procedures aren't followed. There are a number of general checks that should be made during a transformer inspection. For example, if there are more turns of wire in the secondary winding than in the primary winding, the output voltage will be higher than the input voltage. In other words, the transformer will increase or step up the voltage. On the other hand, if there are more turns in the primary winding than in the secondary winding, the output voltage will be lower than the input voltage. In this case, the transformer will decrease or step down the voltage. During the inspection, if any loose or broken wires are noticed, they should be reported right away. Also, the affected area should be kept clear until the problem has been corrected. The casing of an oil-cooled transformer should be checked for leaks and signs of corrosion that can result in leaks. A good place to check is the joints where piping is connected to the casing. When inspecting the transformer's radiators, remove any paper or debris that might be blocking the radiators and interfering with cooling. Monitoring a transformer's gauges can help you detect potential problems before they get serious. Oil-cooled transformers often have gauges for oil flow, oil temperature, and oil level. Now, if a transformer uses fans to help in cooling, be sure to check them for proper operation as well. Excessive vibration or unusual noise may be a warning sign of a problem with the fans. If you see any abnormal indications, report them. In this topic, we examined the basic operating principles of a transformer. We looked at some major transformer components, and we saw some operator duties associated with transformer inspections. Now try some practice questions related to this material. One type of component that's found throughout a plant's electrical distribution system is a circuit breaker. Circuit breakers serve as protective devices, and they also provide a way to isolate electrical equipment from a source of power. When it functions as a protective device, a circuit breaker helps prevent excessive current from damaging circuits and equipment. A circuit breaker is able to do this because it has electrical contacts that open or trip to interrupt current flow to a circuit. When it functions as an isolating device, a circuit breaker is tripped by personnel to isolate equipment from a source of electric power. This allows equipment to be locked out of service so that it can be worked on safely. Here's one type of circuit breaker that's sometimes used in electrical systems. It has an on-off switch. When the switch is in the on position, the contacts are closed and current flows through them. When the switch is in the off position, the contacts are open and current is unable to flow to the load that the breaker is protecting. When a breaker trips, current won't flow through the circuit until the breaker is reset, that is, until its contacts are closed. To reset this breaker, the switch is first turned to the off position, then to the on position. Not all breakers trip in the same way. Some breakers have internal devices, such as electrical coils, that sense excessive current and open the contacts. Other breakers use separate external devices called relays to do the same thing. Relays sense abnormal circuit conditions and send a signal that trips the breaker. One common type of relay is an overcurrent relay. Overcurrent relays protect equipment from damage caused by excessive current flow. Another type of relay, called an undervoltage relay, protects equipment from damage caused by lower than normal voltages. Motors and other equipment are normally rated for a certain voltage. Too little voltage can cause a dangerous increase in current flow. Circuit breakers and related components are often enclosed in separate housings that are grouped together. The housings are electrically isolated from each other so that the breaker for one circuit can be worked on without affecting the other circuits. The housings also protect personnel from coming into contact with the high voltages inside. If abnormal conditions develop in an electrical circuit, a circuit breaker may trip. Before the breaker is reset, it's important to try to determine the cause of the trip so that any necessary repairs can be made. Resetting a breaker without first checking for the cause of the trip could damage the breaker and other equipment, and it could create unsafe working conditions for personnel. Let's watch as this operator goes through a basic procedure for resetting a tripped circuit breaker. Keep in mind that whenever you're involved in this sort of procedure, you should always follow your company's safety regulations. In this example, the breaker that has tripped is used to protect a motor, but the same general procedure can be applied to other circuits as well. First, the operator checks the motor for obvious signs of damage, such as overheating. He also checks to make sure that there are no obstructions that might prevent the motor's shaft from rotating freely. Then he checks the input power cable for signs of damage that could have caused a short circuit or a ground. Either condition could trip a breaker. After finding no obvious problems with the motor, the operator goes back to the circuit breaker and resets it. Then he returns to the motor and tries to start it. If the breaker trips again, he'll report the trouble. He won't keep trying to restart the motor because that could damage the motor and the breaker. The time delay allows time for the motor to cool before it can be restarted. The procedure that we just saw dealt with the protective function of a circuit breaker, interrupting current flow to protect a load, such as a motor. Another procedure, known as racking out a breaker, can be used to physically lock out a load from its source of power so that de-energized equipment can be worked on safely. Racking out a breaker involves physically disconnecting the breaker from its electrical connections. Let's watch this operator go through a procedure for racking out a breaker. First, he makes sure that he's got the correct breaker. He doesn't want to cut off power to the wrong circuit. Then he opens the breaker's contacts using a local switch. Keep in mind, though, that some breakers are opened from a remote location, such as a control room. For this breaker, the operator reinserts the fuse block upside down. This maintains a physical break in the control circuit so the breaker can't be operated. The off label indicates that even though the block is in place, the circuit is still de-energized. Now the breaker can be physically disconnected. Here, that's done by releasing a latch and sliding the breaker out of its enclosure. An indicator on the side of the enclosure shows when the breaker has been disconnected. Often, the controlling link between a plant's electrical distribution system and individual pieces of electrical equipment is a switch. Basically, a switch is a device that can be opened or closed to start or stop current flow in a circuit. There are a lot of different types of switches in a plant, and they can serve different purposes. For example, these disconnect switches are used to isolate circuits in an electrical distribution system. Other types of switches include limit switches, which help regulate the movement of mechanical equipment, and pressure switches, which respond to changes in pressure by opening or closing an electrical circuit. Switches can also be used to help isolate electrical equipment so that maintenance work can be performed safely. Most control panels contain many switches that can be used to start, stop, and position equipment. Switches can also be located at or near the equipment they're associated with. In order to properly control equipment and processes, operators need to know how to operate a variety of switches. Two types of switches that operators commonly use are push-button switches and rotary switches. Push-button switches can vary in design. For example, when some push-button switches are pushed in, they stay in on their own. Others must be pressed and held as long as the switch is expected to operate. When the push button is released, the circuit is de-energized. Still other push-button switches are simply pressed and released to complete an electrical circuit. Push-button switches can have various features, including lights to indicate whether equipment is on or off, and labels to indicate the push button's functions. As long as the button is held down, the equipment cannot be started up from a remote location. Another type of switch that operators sometimes work with is a rotary switch. Rotary switches are rotated to start, stop, or position equipment. As with push-button switches, rotary switches can vary. With some rotary switches, the switch stays in the position that it's turned to. With others, the switch returns to a certain position after it's turned. For example, the normal position for this switch is in the center. Regardless of how the switch is turned, it always returns to the center when it's released. Some rotary switches require a separate physical movement in addition to the rotation of the switch. For example, this switch must be pushed in and rotated to operate a piece of equipment, and pulled out to stop the equipment. Many rotary switches are designed to prevent accidental operation. For example, this rotary switch has a removable handle. The handle can be taken off when it's important to keep the switch at a particular setting. Inside the transformer casing are the windings. The windings are usually mounted on an iron core, which concentrates the magnetic field produced in the windings. In this topic, we examined the basic operation of a circuit breaker, and we looked at steps involved in resetting and racking out a circuit breaker. We also saw how different types of switches operate. Now try some practice questions on this material. When inspecting the transformer's radiators, remove any paper or debris that might be blocking the radiators and interfering with cooling. One type of component that's found throughout a plant's electrical distribution system is a circuit breaker. Circuit breakers serve as protective devices, and they also provide a way to isolate electrical equipment from a source of power. When it functions as a protective device, a circuit breaker helps prevent excessive current from damaging circuits and equipment. A circuit breaker is able to do this because it has electrical contacts that open or trip to interrupt current flow to a circuit. When it functions as an isolating device, a circuit breaker is tripped by personnel to isolate equipment from a source of electric power. This allows equipment to be locked out of service so that it can be worked on safely. Another procedure, known as racking out a breaker, can be used to physically lock out a load from its source of power so that de-energized equipment can be worked on safely. Racking out a breaker involves physically disconnecting the breaker from its electrical connections. Often, the controlling link between a plant's electrical distribution system and individual pieces of electrical equipment is a switch. Basically, a switch is a device that can be opened or closed to start or stop current flow in a circuit. There are a lot of different types of switches in a plant, and they can serve different purposes. For example, these disconnect switches are used to isolate circuits in an electrical distribution system. Other types of switches include limit switches, which help regulate the movement of mechanical equipment, and pressure switches, which respond to changes in pressure by opening or closing an electrical circuit.